Good afternoon, everybody. Thank you for coming and welcome to the public cloud seeding workshop here in Aspen, Colorado, in Pitkin County. We're in the commissioner's room here today, and we have a whole bunch of excellent speakers to cover a pretty complex topic, and that's cloud seeding, wintertime cloud seeding to be specific. And so today, we're going to try to make this a very comprehensive discussion covering all aspects. We are streaming live, and as such, those that are watching online can provide comments, questions, and we'll try to address those as we go. Before we get too far into this, just want to give a brief background on how we got here today, and that is a proposal to expand some of the ongoing efforts that are currently happening across western Colorado on cloud seeding, wintertime cloud seeding, to enhance and augment snowpack. Pitkin County in particular asked the Colorado River District, for whom I work, and I should mention my name is Dave Kanzer. I'm the Deputy Chief Engineer for the Colorado River District. We're based in Glenwood Springs, and we are just the convener, the facilitator of this meeting. This meeting, again, the objective is to provide scientific information, sort of the state of the science for wintertime cloud seeding, and I'm very pleased to have a series of top-notch experts in the field. So today, really, again, to repeat, this is an investigation of sort of the lore, the legend, and the science of cloud seeding, wintertime cloud seeding. How might it help us? How might it hurt us? We are under quite a few challenges in the Colorado River Basin today, and you'll be hearing a lot about how we may use cloud seeding as a tool to address water supply management in the Colorado River Basin. We are rapidly arriving at the every drop counts scenario, and so that's why we're here today to talk about how we can make every drop count. So we have a packed agenda, and I want to pass this over to Greg Poshman, who is the Pitkin County Commissioner. Greg will give us a welcome and the Pitkin County perspective on wintertime cloud seeding.
Great. Thanks, DK. Really appreciate it. Good afternoon, everyone. Thank you all for being here. We are broadcasting live. We've got an audience of maybe 20 people as well as our roundtable. So for a Friday before Memorial Day weekend, I think that's pretty good. A little bit of history, if I can begin. I grew up in Aspen, and I remember cloud seeding first coming on the radar when I was in probably grade school. And I believe it was George Stranahan, a local physicist and founder of our physics center, came in to talk to the class to describe it to us, what it meant, what it was. And that's the first time we heard about it. Since then, I know it's been tried over the years. I know the skiing company made a go with it. Hal Hartman, one of our revered local scientists and practitioners of snow safety, was experimenting with it back in the 90s. And I think the results at the time are inconclusive, which is a pretty common thing to hear. You know, how do you measure this? And so it was abandoned then. It came back to us early, I guess a year and a half ago, when we were looking at a drought situation, and it seems every time there's a drought, cloud seeding comes back around. And so in this year, it turns out to be such a huge snow year, the conversation might not have come up, but we're still looking at what we can perceive as a drought and drying water situation going forward. When I heard that cloud seeding is being practiced for drought mitigation, it occurred to me we all need to understand it better. There's a perception that it isn't done in this valley, when in fact we've had generators in the valley for 10 years. I believe they've been feeding other watersheds and not particularly ours, but yet it's going on here. And historically, I and many others have categorized cloud seeding as a mysterious and even frightening practice with consequences we don't quite understand. And there's a great degree of concern clearly present today, and I think hopefully we can address that. In whatever direction it goes, I don't know, but I think that this will be very valuable to at least help inform the public to the best of our ability. For those of us, including myself, who come to this session with preconceived notions about the danger or the efficacy, the benefits or the unintended consequences, this is really our opportunity to listen and learn from scientists and practitioners who work with the River District and the Colorado Conservation Board and the state agencies on sanctioned programs that are already in existence today. And also we have some local and trusted experts from groups in town that we can introduce as we move forward. I've got some key questions since I'm the bully pulpit here. I've got a couple of key questions, and I think I imagine myself shutting up and letting you all talk. The first one is how does the scale of the risk from pollution from cloud seeding compare to other activities that we take for granted? I know fireworks displays push thousands of pounds of colorful metals and pollutants into the skies 2 or 3 times or maybe more a year over our town, and that has been accepted. Yet there is some trepidation whenever cloud seeding comes up. For other scale examples, our general aviation alone, not the commercial aviation, but general aviation alone at the airport burns 78 million gallons of Jet A fuel over, or purchases that much to burn to fly in and out of Aspen every year. I mean, how does this compare? Going to vehicle traffic on our highways burns millions of gallons of gasoline, and even particulate from wearing tires on our highway and metal parts that come off in wear and tear enter our atmosphere and watershed on a scale that's possibly measurable and maybe even more measurable. I know CDOT spreads hundreds of thousands of gallons of a mag chloride solution on our highways every year. What does that do to our rivers, and how is that affecting us? It seems that we take a lot of things for granted, but once again, when cloud seeding comes up, the red flags go up, and my biggest concern is why. There have been concerns about it being carcinogenic or being associated with chemtrails or things like that. So I think it's time to learn as much as we can, and I'm really looking forward today. So I'm hoping that today's program inspires questions and raises the level of knowledge for all of us. And I'm hoping we come out of this feeling fully informed, and I'm certain we're going to have even more questions at the end of the day that we will have answers. But I think this is a really helpful process. So thank you all for being here.
Great. Well, thank you so much, Greg, for hosting us, inviting us to be here today. And I'd like to continue the program here with our first speaker, and that's Eric Germstadt. Title of his talk, as you may see there, is Colorado Cloud Seeding 101. What is cloud seeding? And Eric comes to us today with over 17 years of experience. He runs owns and operates a firm called Western Weather Consultants. They're based in Durango. He helps the Colorado River District operate our program, and you'll hear more about that. But today, Eric will cover the basics related to the modeling that helps decide when and how to seed, the overview of activities in Colorado, what techniques are used, and we'll briefly introduce the process related to permitting and requirements for cloud seeding in Colorado. So without further ado, I'm going to pass it over to Eric.
Thank you, DK. I'm Eric Germstead with Western Weather Consultants. We have one of the permitted cloud seeding programs in this region. There's 2 permitted areas, and then we have 3 down in the San Juan Mountains as well. Basically, what cloud seeding is the vaporization of silver iodide solution through a propane flame. Then there's a lift mechanism, usually orographic winds, and that carries the silver iodide into the cloud base. where it's then combines with moisture until it's large enough to fall out as a snowflake. And we try and position a cloud seeding network of generators in and around a mountain to best work with the climatological winds that come in through the area to have the snowfall fall out in a not like a small target area, but a pretty large area we're trying to work with. These are the different kinds of cloud seeding generators. Aircraft is used in Colorado, but not very much. It's fairly new. I think the first aircraft program started this last fall up in the northwest section of or just north central state. Mostly what we work with are ground-based generators. We have remote and manual generators. They both burn a silver iodide solution. This is the seeding criteria that we work with here in Colorado. It basically states that when these conditions are met, we're able to light the generators and proceed with a cloud seeding event. There is a specific temperature regime required for cloud seeding, so we need temperatures between -5 and -16 degrees centigrade. And obviously we need to have wind directions traveling over a cloud seeding generator into the intended target area. And we need to make sure that there's no inversions or atmospheric stability regions in the areas that we're trying to seed as well. So a way of looking at this is through some forecasting models. This is just one example of a high resolution rapid refresh, otherwise HRRR model. This provides us an hourly forecast. The Pivotal website that we use has integrated our generator locations and a couple of the target areas, like Purgatory Ski Resort is listed on this one, so that we can track a storm's movement and the intended or expected amount of precipitation to fall in that area. It gives us winds and temperatures at 700 millibars, which is roughly 10,000 feet of elevation. And that's the area we're trying to really look at getting our product, the silver iodide, up into to really get a good effective seeding effect. So from this forecast model that Pivotal provides, we're able to also select a point on the map, which then provides us a SKU-T diagram. SKU-T you can look at to see if there's an area of inversion within that model. So we use this to kind of just do a quick double check to see if we have any stable regions that we shouldn't be seeding into. As part of a seeding operation, part of the permit process also requires us to suspend seeding for multiple reasons. One being if the snowpack in a basin gets to be at certain levels during the year, we don't want to create a snowpack that's just huge. We want to keep it within the extensive normal. So we keep track of the Natural Resource Conservation Service, NRCS. They provide us with some information. This site kind of just has a bunch of snow tells within basins, and they're color-coded, stating what % of normal that snow tell location is at, so we know if we're able to seed in that direction or not. Also, they provide just a chart that shows basin-wide with all the snow tells in it of what the SWEA levels are at. On that previous slide, I defined what SWEA was. Basically, it was just saying if you took all of the snow in a snowpack and instantaneously melted it, it would give you the depth of water that was in that snowpack. So we look at the SWEA readings, and based upon the monthly percentage of normal values that we're able to seed up to, in this case it was 155% of normal for March. I tend to take what they give us and color code. Orange saying, hey, we're reaching this. We might not want to seed into that area if it's going to be a long duration storm. Or if it's red, obviously we avoid seeding into that specific area. And if the whole basin is in a red as far as being over, we will not seed into anywhere into that basin. And then this is what the NRCS also sends out to the Colorado Water Conservancy Board, just as like a double check to make sure, you know, everyone's kind of on the same page. So this is a report that they receive and look at, and if they notice, you know, spots of, you know, we shouldn't be seeding into, they'll give us a call or something and say, please don't seed into these areas. Included in the permitting is avalanche suspension. So we use the CAIC Center, and they provide us with a highway summary. So if there's a avalanche concern along traveled highways, they notify us. Green, you know, clear, go ahead, seed. Yellow is kind of like stoplight, caution, and then red, please don't seed. But we tend to really take notice once we're in the yellow. The yellow has 3 stages: notice, caution, and just straight, or notice, caution, and then just caution. If we get into a notice and we're going to have a long storm event, we tend to, especially if it's going to be an overnight event, we won't seed. But if it's something we can monitor throughout a day and call operators to have them shut down during the day, we might seed a little bit of that storm. But if we reach notice caution, we will turn the generators off and just let everything settle back down until the next storm comes in. So I guess the big question we're trying to answer here today is cloud seeding safe? Yes, it is. There's been a lot of studies conducted showing no effect. The position statement by the Weather Modification Association is stated there, and it just says that there's no environmentally harmful effects arising from cloud seeding with silver iodide. We'll get into this a little bit more later. Continuing safety, I went over the suspension criteria a little bit with the permitting that we have to get. So again, there's the percents of normal based upon months that we use here in Colorado. And also, again, just stating who we work with for the highway suspension criteria. Moving on a little bit, as Greg said, there's been a few programs in the Aspen Valley in the past. 76, 78, there was a large drought, so we were asked to come in and have a program which lasted for a couple of years. And then again in 1993, Aspen Ski Co. wanted to give cloud seeding a try, so again we had a couple years of working with them, and then that program has ended, and now we're in the process of deciding if cloud seeding in the Aspen Valley is something we'd like to move forward with into the future. Regional programs, again, Vail, Beaver Creek ski areas have had a program since 1975, and CCMRB, Central Colorado Mountain River Basin's program, they've been active in the region since 2012. This is a map that basically shows the CCMRB program. It's mostly seeded within the Blue Hatched area, and Vail and Beaver Creek ski resorts fall within that. We've done a little bit of seeding up towards the Granby area in kind of the green outlined section. And then where that red section is down lower, that includes a little bit more of the Roaring Fork watershed. So we do seed into the Roaring Fork watershed right now a little bit. And this is what we would like to include with the, potentially coming up, would include more snow mass, Aspen Mountain, and a little bit more of the Roaring Fork drainage. Some informational websites in case you wanted to look up some more information on cloud seeding and kind of what CWCB oversees, or any of that kind of information is available here. And with that, I'll send it back over to DK.
Great. Well, thank you so much, Eric, for that quick overview. As you can tell, there's a whole bunch of issues to talk about, to consider. And as we drill down here from sort of the 101 cloud seeding level, we're going to welcome Dr. Tom DeFelice. Tom is a well-known expert in the field with over 30 years of experience in atmospheric science. He holds a doctoral degree, a PhD in atmospheric science from North Carolina State University, and it comes to us today from Sheboygan, Wisconsin. He flew in, brought some weather with him, and I should note a few things about Tom and his perseverance. As you may all know, this workshop was originally designed and scheduled for March 13th. And that, you may know, was a day that Mother Nature may have been playing some tricks on us and dropped the bomb cyclone and prevented Tom from arriving and preventing us from having this meeting. And just yesterday, after waking up at about 4:30 in the morning in Wisconsin, in Milwaukee specifically, to get here, he found himself pretty much stuck at DIA because the high winds and the weather and Mother Nature's tricks. And as we all know, we got quite a bit of snow, and it seems like every time we try to do this and talk about cloud seeding, we get natural snow. So, many people say, maybe we shouldn't be messing with Mother Nature, but in fact, she's messing with us, I think. But with that introduction, Tom will be helping us understand sort of a higher level understanding of cloud seeding. He'll be talking about research that addresses the environmental impacts and what we call extra area effects, what happens downwind, essentially, from cloud seeding, what happens to the silver iodide once it enters the environment, what materials are used, and what studies are the basis for what are now standard practices for cloud seeding. So with that, I want to have you welcome Dr. Tom DeFelice of CU Boulder.
Well, hi. Tom, can't beat that introduction, yes. Although, I was beginning to get a complex almost about coming into Aspen. I love Aspen. It's been almost 25 years. Perhaps that's why, since I've been in this area. But I wanted to say that the comments that you hear now relative to this topic are my own personally. They don't necessarily represent the views of the CWCB or CRD or any of my other constituents, whether they're in Wisconsin or somewhere else. And let's continue on here, and I want to give a shout out to DK and Joe, and of course the Commissioner for inviting me, of course staff as well, and my co-speakers here. Some of my mentors are listed down below. Hope I'm not blocking it. Here's my talk, a little bit of an introduction, including now. Cloud Seeding 101, I have to expand a little bit upon what Eric had said, because this precipitation process that we're basically talking about is a little bit more complicated than might meet the eye, and I'll show you in a minute. And then we'll hit the concerns, as DK pointed out, and then I'll start to prime the discussions for social and economic benefits of cloud seeding and a future need, at least in my view. Okay, first of all, what's the purpose of cloud seeding? In my opinion, cloud seeding activities are designed and implemented for the purpose of positively affecting the natural precipitation process with respect to the safeguards established by the regional concerns and avoiding as much as possible damage to public health, safety, or welfare and to the environment. That's the message or the meaning and mantra that I was given back as a young student, an undergrad. So moving on, there's no quiz. This is a terrible slide. And any one of my professors, including DK, is starting to get on my case about it. This is the precipitation process. And this is a simplified version from back in '74. And yes, I do know the authors. I did meet them. So I'm not going to spend any time, but it takes us from the nuclei and some of the particulate matter that was mentioned, and gets that involved in the cloud process, so they become incorporated inside the cloud system, and then they precipitate out. And then there was a middle part there that I'll kind of show some pictures of that, because those are key to the precipitation process. Here, this diagram is another busy one, but what I want to show here is just point out some things here. And these are atmospheric constituents. And, okay, wait a minute, guys. I have to, whoops. Hey, how did that happen? They didn't give me a little tutorial on how to use the slides.
What are you pointing it at? That's the question.
I don't know.
What device does he have to point at? Oh, DK's got it.
Oh.
He's running it.
Oh, okay. DK, you're the man. All right, so we went on to this one. That little part in that square, we're going to, or rectangle, whatever it is, we're going to look at. And I wanted to do the pointer, and I guess this is the pointer. And on here, it's a little bit different. Okay, so we got the size of the constituents in micrometers. Hair is about, and it's on there, it's about 80 micrometers on the average for the average person. Okay, so just to give you a reference sake there. And anything from about 1 microns and to the left are nuclei. Okay, they're atmospheric constituents that, you know, in that previous diagram you had nuclei mentioned. And then from around 1 or 2 microns and above, you get into cloud droplets and then precipitation. And another thing that I want you guys to take away from, besides the notes on the right, is that you got smog, you got tobacco smoke, oil smoke. Not sure where that came from, the tobacco came from. Sea salt crystals, CN and CCN, which are highlighted, I'll get to that, and clay. But there's different compositions in this particular size range that might become important, and I'll get to that in a minute. But the CN is not it stands for condensation nuclei, thank you. And it stands for condensation nuclei. And right there, but it's not the complete range of condensation nuclei, because bacteria and viruses and insecticides, clay, they all come in under that category of condensation nuclei. So let's go to the next slide here. And when we talk about nuclei in the atmosphere, they can be binned into 3 categories, particularly relative to their composition: hydrophobic, hydrophilic, and hygroscopic. Now, hygroscopic, you know, those are the water-loving nuclei. Those are the ones that are most likely to act as the seed to form cloud droplets. Hydrophobic, well, I know everybody knows the words, but these make the best ice-forming nuclei, such as silver iodide, for example. Hydrophilic is in between. Some are good ice nuclei, some are good condensation nuclei, or cloud condensation nuclei. And one thing we could say from that past diagram and this composition, and from the data that I cannot show and do not have the time to show, we can spend 10 years studying it, that nuclei are chemically homogeneously heterogeneous. What does that mean? Okay, I know, I'm showing off, but not completely. That means that if I were to go into the atmosphere and sample any particulate, assuming I could do that, and theoretically it is possible, by the way, I would find that it's not just a single compound. It's not sodium chloride. There's more than one salt in those nuclei. There's sodium chloride, there might be ammonium sulfate, there might be other species or other compounds that are in there. Hence, if I go and I pick 1 or 2 or a whole bunch of them now, I would get the same story, a very similar story. So they're not pure. Some might be, but most of them are not. And 1,000 to 150,000 nuclei can fit in the volume of an index finger. I thought that was an interesting concept. So it's hard for us to see, but they can be very important. And so I don't have to go through this as much, but we got to get these nuclei into a cloud, into precipitation. And so we need 3 things. We need moisture. We need the water-loving nuclei, so the surfaces for that moisture to collect around. And so if I can get you into the environment, and you know, we're outside, we have, you know, nice weather today, and the nuclei are out there, and the water vapor molecules are, you know, kind of moving in the vicinity of the nuclei. And you'll see down over here that this nuclei here is likely a water-loving nuclei because there's a lot of water molecules around it. This one might be in between, and this one kind of bounces off, but it might stick. That's hydrophilic, etc. And we need a trigger. We need a trigger to bring enough water vapor molecules to the nuclei to help them grow into cloud droplets. Okay, now the trigger could be the mountain, like Eric pointed out. It could be a frontal system or, some other trigger. And we can go into details later on offline if you really need to go into it. But we have cloud droplets. And let's say those cloud droplets come into the part of the cloud which is below freezing. And if the cloud has droplets below freezing, they are called supercooled cloud droplets. And as you see here, we have the droplets, and there's a lot of vapor molecules on them compared to over an ice particle because we had a nuclei, whether it was natural or silver iodide or whatever, nucleated an ice crystal. Here we're at minus 15, so it could be either. The ice crystals in time grow larger as the more water vapor molecules go to that surface. They go because there's a high amount of water molecules here to a low amount at the surface of the ice crystal. That's a natural process. Things go from high to low. A lot of chocolate chip cookies to a little bit chocolate chip cookies, especially if you're me. Not that anyone would know that around in this group here up front. So it is said that ice crystals grow at the expense of the supercooled droplets, but really, ice crystals grow from the water vapor from those supercooled droplets. So just keep that in mind. And so now we have ice crystals, and they're big enough to form as precipitation. But if I continue, or we continue, the theory says we continue to grow by this deposition growth of the vapor attaching to the surface, ice crystals in our case, could be water, but we don't care about that right now because we're talking snow. It would take about 1,000 or more hours for that ice crystal to fall down as precipitation. Well, observations show that it could be tens of minutes, maybe an hour, for that process to occur. So there's some inefficiencies there, perhaps. Anyway, there's data, by the way, dating back to at least 1950s that support this claim. And I'm not going to spend any time on this. You're welcome to ask me questions or slow me down later on. But remember I said that there was this middle part of that this complex process of forming precipitation? Well, here it is in simplified form. You have that, the deposition growth, we know that, we got the crystals, and they start collecting other droplets, or they start collecting other ice particles. That's called aggregation if they collect ice particles, or accretional growth if they collect droplets. Now, if I see an ice particle that's grown by accretion, I look at it, I say, oh, that crystal was rimed. So riming is a process. Some might interact between the two and get some splintering of particles. There's no quiz on this, and I don't want to spend too much time on this, but I do want to set up the next slide. But let's take a look. There's a nice artistic rendition of accretion and aggregation here by West Publishing Company. Is a 100-level book that I had borrowed from. And here is an example of the ice crystals growing, collecting the droplets, accretion or riming, and then grapple particles, which we can get a lot of, kind of breaking down the smaller, more fragile crystals. That would be splintering. And each one of those little crystal parts then grow by the same process I just outlined. And so then you get more crystals going through. But as these particles, once they get enough mass, they start falling through. They start collecting and sweeping out all of the other droplets below them or in their vicinity as they fall. And this growth rate is proportional to their size. It's probably squared in most cases. So that helps speed up the growth time and why we see precipitation within an hour, not according to the other way. So this is a complicated process. It's not linear. And because it's not linear, it's harder to quantify. But our models do pretty well, except for when you want to go into Aspen to do this webinar. That might be something else. Here, I want to just outline you that, okay, we have fog droplets on you have time to fall a certain distance, say about 1,000 meters or 3,280 feet from these hydrometeors, and the longest time to fall that same distance would be fog, and this is just a theory. Then drizzle, and then heavier rains, take the shortest, they fall quicker, obviously. Drizzle and rind ice crystals, they take the same amount of time to fall the given distance. And we can go into the physics and the aerodynamics of that if you wish. But right now, that's an important concept. Fog droplets, for example, stay in the sky longer than the precipitation does, which makes sense, right? Also, a common misconception is the shape of the rain droplets. I will not spend any more time except to say they are not drip-shaped. There's studies to support that. So let me summarize. We get the nuclei, the water vapor molecules, get them going as far as the condensation into droplets. As they go up in the sky, because it's lifted by the mechanism of our, topography here in town or nearby, or there's instability in the air. They make cloud droplets. You get cold enough for ice crystals to form, usually around 12 degrees Fahrenheit, or -5 or degrees Celsius, or about 26-ish degrees Fahrenheit. If you have silver iodide, it starts to process sooner. That means you can get more nuclei. And then they get big enough, they fall out, and they fall, in our cases, mainly as snow, and then they might melt in the valley. I fixed that one for you, Dave. Anyway, precipitation efficiency is the ability or how well the atmosphere takes the vapor and converts it to precipitation. That defines precipitation efficiency in the simplest sense. And yes, it can be affected by pollution. And there's been studies by it that more comprehensive that I've seen and perhaps relevant to our cases because it was done in the Sierra Nevada or in that area, was Rosenfeld et al. But there's other inadvertent effects that could contribute to the precipitation process, and some of which you have mentioned. Now, what if we see the cloud and we insert silver iodide into the cloud? Basically, all I want to point out here is that we're increasing the probability of adding ice crystals to the precipitation that that might or might not naturally occur. So that means more precipitation on the ground. And the targeting of where that precipitation falls, Dr. Sarah and Dan, and perhaps a little bit of Sean will touch on that and go into that in more details. But that injection of the silver iodide, can come in a couple of different ways. Eric mentioned ground-based and a little bit of the airborne, but the airborne, either by burning the flares or dropping dry ice or a solution using a device similar to the ground-based, but obviously made for aircraft, because the FAA has to inspect the aircraft. So we'll get to that later. But now, we have enough of a background and a reasonable feel for how complicated this precipitation process can be and why it might have delayed this meeting once or twice. And let's talk about cloud seeding and whether or not it robs Peter to pay Paul and Mary or causes a drought, so on and so forth. So what we did, a bunch of us took a look at the available data, and on the top we took the data and we binned it into natural non-seeded clouds, and then we took that same cloud and added with some information from some seeded clouds. And the information were, as Eric pointed out, we had sounding data, we had data from thermodynamic diagrams and other variables from those diagrams. We had observations, radar data. We had in-cloud microphysical data. We knew what the droplets were and how they were distributed according to size. And we had ice or not. And we took also Bram's data in 1952, which came up with the original water budget. And this is what became. The red here is vapor. So the vapor of a cloud system was about a little bit more than half, 51%-ish of it. And there's large error bars on this, but conceptually, it's representative. 40% was involved with the liquid component, the droplets or maybe ice particles, depending on the type of cloud. But it's mostly droplets. And 9% of that, in the natural case, was due to the precipitation hydrometeors and their fall to the ground. There was no seeding, so that's 0. And that's in green. I'm sorry, that's in purple. Okay, so that's great. Now, knowing that the clouds form, and this is an overall life cycle representation of the water budget of a cloud system. So then we took that same cloud system, and then we figured in a conservative way, what if we seeded that cloud with silver iodide or any material? It didn't matter. We were going to increase the precipitation. We took the scientifically relevant, most conservative estimate of, or scientifically acceptable, most estimate of how much of an increase our cloud seeding technology will provide. And that is represented by 1% in this lower case. And since ice crystals that are, the extra ice crystals that were formed grow at the expense of the supercooled liquid water content, our data suggested that, well, it's coming from the cloud droplets themselves and that component. The vapor, because of equilibrium considerations, stayed about the same, and we had the 9%, from the nature. So if we were to say that cloud seeding caused a drought or dried up the atmosphere, then we would see a much different profile. We would see a lot less cloud left over after the precipitation process. Or if we were completely physically based in the ideal world, then there might be no cloud droplets at all. That's not the case. These cases are more representative. Cloud seeding does not likely dry up the atmosphere on at least regional scales nor cause droughts. We would like to get more data to verify that, of course, but with what we know now, this does not happen because it would be more obvious, and even in this simple energy or water budget scheme.
Tom, real quick, is the at least regional scales, is that in there just because there's no data on larger scales of regional right now?
Yeah, I saw something on yes, mainly, because that's just from the cloud seeding projects, and that's kind of a regional. I saw something on a climate scale, and it was more theoretical than not, and we talked theoretical, offline. But,
Thank you.
yeah.
Remember to just to repeat the questions when we have an opportunity next
Okay.
time, just so the audience can hear. Yeah.
Okay, did everybody hear that? Because I could read. Okay. So I'm new at this part here. So if I want to put this, the previous diagram into physical sense real quick, then on the left would be the case that was seeded. And as I said before, the precipitation would fall over a certain area and be, of limited density as far as the precipitation. It'd be a certain amount, okay? But in the case of the seeding, we'd have a little bit more densely covered area, okay? And that would imply or translate to more precipitation, and it's spread over a larger area. And to see that better, I just put this here to show that there's a little bit of a enhancement due to the precipitation. So basically, cloud seeding benefits Peter, Paul, and Mary, does not dry up the atmosphere nor cause drought, and additional studies should be conducted to verify the conceptual model and to supplement with the limited amount of observations that we do have. And that started, by the way, because in 2016, our colleagues up in the Wyoming area, Jing et al., have basically found observational evidence of precipitation enhancement downwind of the target mountain. And I know there's another study that's about to begin, if it hasn't already, overseas. I think it was in China or one of their provinces that are trying to mimic this study as well. So we're putting silver iodide into these clouds, more silver iodide than nature would have allowed. So what effects does it have on the environment, and is it toxic to that environment?
Can I ask a quick question?
Yes, sir.
Can you come up to the mic?
Come on up, welcome to.
Oh, I didn't want to do.
Uh-huh.
You do have a hand mic, perhaps, also.
Just quickly, it looked like from the pie chart that it doesn't rob Peter to pay Paul, nor does it do anything, because there was just 1%. So, and is that 1% significant or no?
Well, the 1%.
Treat to my.
Well, the question is in that previous pie chart was, is that, a significant difference or not? Based on the data that we have, one would have to say it's one or two, or, it's a handful of data points. So if you look at the statistical significance, we need more data. But, I'm sorry, I was.
On that too, because the pie chart was meant to represent the entire water vapor budget. So I think in your estimate there, the natural precipitation efficiency is only a fraction of the amount of water that condenses into clouds to begin with, and that was that 9%. So I think you're using an assumed 10% effect of additional precip to get that 1% extra. So that 1% is assuming a 10% relative to the natural precipitation that would have fallen. The question still remains, is that significant and cost effective and so forth? But just to clarify that the seeding effect assumed in that pie chart was a 10% effect, and it's just 1% or less of the overall water vapor in the atmosphere on that regional scale.
Okay, thanks.
Thanks. Any other questions?
I want to, if I could, pardon me, I wanted to just confirm that I understood that the 1% is the percentage of the available, you said, in the environment, which means what's available in the atmosphere passing over that region at that time. So it's maybe 1% of what's available in the atmosphere above could fall as a greater percentage from what would normally precipitate on the ground. Is that right?
Yeah.
Thank you.
So, yeah, so the idea is that, given that overall water budget in the atmosphere of water vapor, you have this flow coming in, impinging upon the mountain. Just because you condense some of it in additional precipitation forms, you still have this ongoing flux of moisture coming in as well. So it's really, the idea is there's this constant flux of moisture coming in, and at any given time over this regional area, our best estimates are that you're perhaps reducing by 1% that total water vapor that would then blow downstream and be available to extra areas as well. So it's a very small fraction of that overall water vapor that is needed for condensing clouds to begin with and forming precip elsewhere.
Right. It was meant to be a conservative estimate. Okay. Thank you. Any other? Okay, so let's continue on then with silver iodide. Now, there's 2 slides of presentations or references for this on this presentation about, I looked into it, I found 77 references on this topic of the silver iodide toxicity that were all relevant. And actually, I was told a couple of months ago by Rick Stone that there are a few more that I've left out. But I did since look at them, and they didn't change anything anymore. But that is the available literature. But there's also been some recent studies by parties independent of the WMA or the American Society of Civil Engineers, Environmental Water Resources Institute, Atmospheric Water Management Standards Committee, or other cloud seeding program sponsors. And they come up with the conclusion that silver iodide from cloud seeding conducted during the last 7 decades has not been toxic to humans, terrestrial, or aquatic environments. So let's, that's the end of the story. That's what they found. But I dug into it a little bit more, and I looked at the Colorado Department of Public Health and Environment 2016 assessment report on potential non-use of Colorado waters, et cetera. And I found that, 21st of the 25 causes of or contributed factors towards potential non-use of our waters here in Colorado were due to silver. Oops, wrong one here, right there. Arsenic, was the biggest culprit. Here's lead. That was another big culprit. pH was kind of in there. DO was dissolved oxygen, by the way. So silver here, when I looked into it, I'm going, wait, silver, wait. Whoa, I got very concerned. They're talking about silver ions. Okay, just wanted to know. And looking in the report further, I'm going, okay, so where is this, where are they getting this data from? And they broke down the affected water bodies into 2 categories, perhaps more, but I only took 2 of them. Affected rivers and also the affected lakes in the region. And when you look at that, interesting pH being about 6.5 to 8.5, by the way. But when you do that, it looks like over here, silver just basically affects in the rivers. Well, that got me interested. Why not in the lakes? Maybe a dilution effect, I don't know. But that's silver ion, okay? And so, you know, looking at that, okay, affected silver. And I looked into the NRCS soil surveys, which, by the way, get the soil pH around 6 and 9. Interesting. But I also mentioned a lot about Pitkin County being a mining area for silver and zinc, et cetera. So, since it's in the rivers and it's silver, you know, silver, I'm not pointing any fingers, but it does point to the fact that maybe the silver is coming mostly from metals. There's a large, but I'm going to this. The bottom line here is that you have a large amount of silver ions in the background. And that means that in order to distinguish the silver iodide from cloud seeding from the background, you need trace chemistry analysis of the seeded snow in the target area and control areas. That it must be done. Okay, and yes, part of my talk in this case is to rally for things that I think could help us out, and that is one of them. So, fact, no ifs, ands, or buts about it. And I'm saying this, you know, from what I read and what I know and what I was taught. Silver ions are definitely toxic to humans, terrestrial and aquatic species, in order of increased toxicity, actually. And there's some relevant studies compared to the kind that we're doing to mentioned here. William Delholm and our colleagues down in Australia have done a similar project that we're doing here that also verify this and cite more references. Okay, behind this statement. No ifs, ands, or buts. Silver ions definitely are toxic. And if you have a lot of silver ions in the soil, as this free silver ion concentration goes up, that actually is related to how much dissolved organic carbon and chlorides and the water hardness related materials and even organic matter might be in this particular area. So if you have silver ions, however, in whatever concentration you have, that water is going to be toxic, going to have silver toxicity. But if you take that same amount of ions and put it in soil or sediment that has organic matter within it, then it won't be as toxic in comparison. I'm keeping the amount of silver ions the same. Okay? That's just a little bit of background and understanding about silver ions and their interaction with the environment. In this case, it seems to be more aquatic than not. pH, I mentioned a couple of times. Okay, pH of 7 and lower is acidic. pH of 7 and higher is basic, right? Pure water has a pH of 7. Pure water with the CO2 that's at a typical concentration on the average in our atmosphere has a pH of 5.6. I measured rainwater that had 5.4, but I also measured rainwater that had a pH of 2.4. Pollution, by the way, was the culprit there, or pollutants were. pH of 3.1 or lower has a tendency to be toxic or harmful to vegetation, and even studies show that, at least for vegetation, if you get long enough doses of pH at 3.5 for long enough periods, and I don't remember what the periods were, but they were at least a year or so, you can have a negative effect from that. Might not have been as bad as 3.1. And it's something to keep in mind that, yeah, from here up, we just talked about the silver ion concentrations. Okay, well, I just wanted to mention that there's other ecosystems and there's other bodies of literature that we could draw upon to help formulate a nice plan to ensure that the silver iodide from cloud seeding doesn't affect the environment in a negative way. Silver iodide. It's has a molecular lattice of like water. It's an effective ice nuclei, especially around -5 or colder. It does not dissociate in the environment. There's no concern about adding silver ions to the environment according to a PG&E 2011 report, and they claim to investigate, a little bit further the dissociation aspect of the silver, in the silver iodide, and they didn't find anything. But silver iodide as a compound has no charge. It doesn't bond with other molecules of concern, if any, and there's no buildup of silver iodide in animals. And silver ions are a different story. We just went through that. I'm not going to bore you with that details. I will say, though, Environmental issues from cloud seeding are accounted for as part of our standard practice documents, and that's just the ANSI here is the American National Standards Institute, as I already mentioned, the rest. SP 42 is the Precipitation Augmentation Standard Practice, which is relevant to cloud seeding here in Colorado. Also, our regulators require environmental impacts, and that's not only from a physical sense, but it's also from a chemical sense. And in that environmental impact or the chemical component is where we provide, an opportunity to check ourselves or consider the potential for toxicity to the environment from the seeding material or other activities related to our seeding. The other way that we do that is by sampling the snow and look for silver iodide. Now on the bottom, I put this up. This is the snow sampling procedure. This was before my time at my master's, which was at Desert Research Institute, University of Nevada, and getting closer to the point, although I don't ever remember it being that close to the snowpack, by the way. I came around in this area here, okay, and lately now, they used their sampling method is a lot better, because when they sample the snow for trace amounts of silver, they want to make darn sure that there's no contamination, because that data point has to be physically real. So I mentioned this before, but we need very low silver iodide concentrations, to monitor, okay? 0.01 parts per trillion is the latest capability of the instrumentation used by DRI, for example, and other labs. And I'm not going to beat this too hard, but you need ultra-clean procedures to be maintained at every step to avoid contamination. And you need to know, the local earth crust tracers and other tracers and what their concentrations are in that materials to help clarify. There might be more to this. Is there a question or additional comment?
Yeah, when you do sampling, they don't actually sample silver iodide. They actually silver, don't they?
Yeah, what they do is they take the sample. Thanks. So the question is, they don't actually sample for silver iodide, but they take the snow that from the target area, and they very carefully, prepare it, and they put it into the atomic absorption analysis or spectrometer, and that identifies silver, trace amounts of silver. And then what they do is, from the reading that they get, they adjust it based on the molar, if I got this right, the molar ratio of silver to iodide, for that compound, and that's how they get silver concentrations, or the equivalent silver that would be if it did dissociate. The silver iodide doesn't dissociate in the snow.
And that's all, just to clarify, that's also why they take other crustal measures, is to kind of, if there's a lot of crustal material in the air and you have higher levels of silver, it's probably due to the crust, or from like around here it'd be silver just from rocks and stuff, because other crustal metals would be elevated as well. Is that correct?
That's correct. So basically the comment was, and to enhance the bottom point here, is that since silver could be part of other clays or kaolinite or other soil matter, then they also analyzed the for earth crustal traces to ensure that any silver that was detected was either from one of those crustal components or those sources or not, for example. And if it wasn't, then that's good. Then you're more confident in the result that you get, that silver was definitely given towards silver iodide. They also used some other tracers of cesium and indium to help rule out the possibility, to help ensure that the silver that was measured in the sample analysis was due to either the nucleation event into ice, in which case they know that silver definitely came from the precipitation that fell in that target area.
So we're looking at 0.01 parts per trillion?
Yes.
Is the sensitivity of the measuring device?
Yes.
Thank you.
And it has, and then also, so it's not only is it the sensitivity, it's also the threshold amount in the that is needed in the sample to be there. So, but it is probably the same in some cases. We'd have to defer to the expert that actually does it to get a clearer response. That's my understanding.
Great, thank you.
Yep. Here I just wanted to show a couple of samples of some of the results of the sampling. And so these are typical examples, not only for the amount of silver in the snow from these analyses, but also typical examples of how measurements are made. And on the left, this is multiple storms. And so the vertical axis on both of these plots is silver concentration in parts per trillion. And on the right, it's 0 would be the surface of the ground, the mountain, right? That's like now. Here, no snow. And then on it increases on the right. So I think that's about 2.5 feet base at this point. And these peaks here, this is a seeding signature. Here we go up here, it's a seeding signature. Most of the seeding signatures lie between 40 parts per trillion and 80, but there are some like here that are a little bit lower, around 10, 15, 20 in all. I want to also say that because of the variation in the wind field and the gustiness, like the gusts, for example, that kept us from coming into Aspen yesterday until later on in the day, that you'll get different parts of the seed plume from the generators because they're single source plumes, and you look at that dispersion. So since the wind varies, the direction of the plume then is slightly changed, and you get this meandering of the plume over the particular target area. And so in some cases, if you're in the center of the plume, which is mostly in this area, where you might get an edge of the plume sometimes. And this is just one sample within the entire target area in this case. I just shown it to show an example. Same thing with a single storm and the temporal variation throughout. We notice again, here's a seeding signature, and I think right over here there's another peak. The meandering, to show the meandering of the plume. Okay. So what I did next was I took the water quality standards and the drinking water standards, as shown, EPA had the drinking water standard, and most state governments have their own, and some of them have adopted the EPA guidelines, and Hendricks et al. Was the author of the silver ion concentrations in this standard. And these vary, according to globally or country or local scales, but that's 50,000 parts per trillion and more are considered toxic. Okay, 100,000 for the water quality standard, but that does vary. And if you looked at the maximum concentrations that we found of silver equivalent in snow after seeding, and did that over 30 years, took all the data and averaged it, we get tens of thousands of data points. The average comes out to just under 10 parts per trillion. Steamboat Springs, for example, here in 1969, it was the late 60s, Perungo and Robertson, they measured parts per trillion of 10 to 8,000. Now the caveat here is, it was 8,000, I looked into it a little bit more. There was a small sample size, so that caused it. But we also have to worry about, in this particular case, the sampling methods and techniques were not very well established. This is one of the studies that gave the impetus for the crew, who my master's thesis advisor and his crew, to improve the sampling procedures. Okay, there's also something else to consider in these data points, and it makes it hard to compare, but you also have to look at the size of the precipitation system, the size of the water bodies in which you're trying to target, and also the loading of the snow as well.
Could I ask a question first before you move on? Number 2, the 30-year average of max concentration. So annually it was less than 10. Is that what that means over a 30-year period?
Yeah, so basically what what I understand the WMA 2009 statement did was the person that put that together, they took the maximum concentrations of the seeding materials for each event. Okay, and one day it might be 20 parts per trillion. Maybe it was 80, maybe it was 40, maybe it was 5 because you only had the edge of the plume. And over the 30 years, they took all these data points and they averaged them. So that value was 10. I mean, there's a standard deviation on it. I didn't put it, but I figured 10 was the point. But even in the worst case where the contamination was, even if that is a good data point at 8,000, we're still well below the standards that are considered harmful or that are needed to be, values need to be below so we have, we protect human health, et cetera, or our environment.
Thanks for that.
Yeah. Any other questions? I know I'm going through this really quick, but
Audience questions, concerns? If there's a microphone up there, if anybody would want to add anything. Okay.
So just to close that up, based on this data that we found in these studies, silver iodide use during the last 7 decades has not yielded any detectably toxic effects, but I do recommend trace chemistry component to the Aspen seeding program, and all of them really, to help ensure that there's no toxic effect, and that remains so. And there's some thoughts on possible sampling that I've gotten from Arlen Huggins at DRI. I think he might have just retired, and other personal communication with those who might have taught me and others, Rick Sohn, for example. And you can either go from, a very simple, get a couple of data points and, get a nice idea about it, maybe good for a proposal, down to, hey, let's do it, double tracers, use indium, use cesium, use the crustal elemental tracers, get, really do it right, perhaps, but then you're talking about at least doubling the cost of the seeding operation itself for a season. I recommend, at least just get the typical method to start with, because that'll get you a good assessment of targeting frequency and spatial coverage of the targeted material, but also whether or not, a good idea of whether that silver is from the silver iodide and not from, local sources or somewhere else.
Can you take away the overlay again so we can see what
Yes, sir.
typical says? Right, okay.
Yeah.
Let's have a picture of it. Right.
And I can make these slides available if DK hasn't already done that or
Right, thanks.
whatever. Okay. So, I'm going to just say a word or two on socioeconomic benefits and then, go on.
Before you go on, can I ask some questions? Is now a good time?
Yeah, come on up,
Should I-
April. Bring your microphone right there. This is April Long.
Hi, April.
Thanks. Hey, I'm April Long. I work for the city of Aspen and the Clean River program. So it looked like one of the slides that you showed. Do I need to use both of these?
Oh,
Or
no,
should
you
I do-
could, yeah, you use the one that's on the table.
That one's muted
If the
anyway.
lights on, yeah, great. No problem. If the light's on, you're good.
Okay.
Thank you.
One of the slides that you were showing at the very end was about the concentration of particles and the levels set by the EPA for water quality standards. Okay, so that's the concentration of silver iodide that would be thought to cause an impact to aquatic life or to human health. Is that right?
Was that?
It was near the end. Yeah.
It was the concentrations with the 10
Yeah,
parts per trillion.
the parts per trillion concentration. Yeah.
Right. Yeah, that actually was the silver ion. Is this it? Okay.
That's actually for silver ions.
That's for the, okay. So for the water equivalent, that was silver ion. In the case of the silver iodide values, what they do is that is the parts per trillion of silver, okay, equivalent, okay, in the snow sample. Because
Okay.
it's silver iodide, but atomic absorption spectroscopy that's used does not detect the iodide component of it. And so one has to adjust, well,
Wait. Just, can you say it simpler? Like, what is the difference between silver ion and silver iodide?
the difference between silver ion and silver iodide is the structure of the compound. They're different compounds.
Different compounds.
The silver ion is mobile in water, so it's free bonding. Silver iodide is not. Silver iodide does not bond with anything else in the water system, but silver ion does.
Which is concerning. The silver ion is concerning because it could bond with other pollutants,
Exactly, it's concerning.
making it more, right. And silver iodide, less concerning because it's not going to bond with anything.
That is correct.
Okay.
As far as we understand, yes.
Okay.
Okay, that hasn't changed. So what is done is the system measures the silver in it's the total silver in the
Total
sink.
silver.
And
So silver ions and silver iodide both show up when you measure that.
yeah,
And it's hard to detect the two differently.
yes.
Okay. So you can assume when you get a silver amount in a parts per trillion that you've got a little bit of both.
Well,
Which is why you need to use, well, I think it's why you need to use proxies like crustal amounts, or time series where you know there's seeding being done, to be able to say one is due to silver iodide,
Yeah.
and the other is probably silver ions or natural
Free silver, yeah.
crustal type stuff. Yeah.
In an area like Pitkin County and Aspen where we probably have silver in our background.
Exactly, and the same thing I'm thinking of like in Wyoming, for example. You know, the background level is tens per parts per trillion, and so you get a value. Say on his one of his examples there, you get a value that's 20 or 30. You say, well, is that just a little more crustal stuff got in the air, or is it from part of the plume of a seeding event?
Right.
And so you have to kind of to tease that out. You have to use these proxies of a ratio, for example, a ratio of what's something that's in the crust, and then if that ratio is very high, then it's silver iodide. If it's low, it's still crustal type stuff.
Okay.
Or better yet would be to use a tracer with
Right.
silver iodide.
So much easier.
And then you'd have both of them together and say,
Right.
oh yeah, it's from seeding or not seeding.
And then,
So
Go
I might
ahead.
add a little bit to that.
Sure.
So that, Dan, would identify the source of the silver that you're measuring in the snowpack.
Yeah.
Was it of a crustal source? Was it from
Or seeding.
a seeding event.
iodide-based seeding?
Right.
But I think maybe the nature of your question is, and what I've been worried about or concerned with as a practitioner early on was, all right, I'm putting silver iodide out there. Could that be a source of free silver that could have toxic effects? And I think it's pretty well established in the literature that silver iodide is insoluble in water.
Right.
So it will not dissociate. It does not become a
pretty
source of free
stable.
silver ion
Right.
in the environment. So it's really not anything to worry about
Right.
as far as a source of free ionic silver in the environment.
Right.
And to find free ionic silver in the environment is almost impossible. It wants to bond with something.
Yeah.
And there's plenty of things in the natural environment for it to bond to. So
Yeah.
it's really a toxic concern in a laboratory setting, but it's really hard to find it outside of a unique setting in the natural environment. You might find that it'd take a pretty special setting to do that.
Right. Yeah. I appreciate that. And then one other thing that I wanted to point out was that you showed the slide of the state's list for pollutants of concern for impaired water bodies. And the rivers in the Upper Roaring Fork and its tributaries are not on that list for silver. And they are on that list for aquatic life impairments. There's a section in the city of Aspen that is. So anyway, just something that I wanted to point out, that given that we probably have a high concentration of silver in our background, it's still not high enough to list us on that impaired water body list. I have a couple more questions, but I don't want to take up a whole lot of time, so.
That's why I mentioned, that's just trying to make a point, and
Yeah.
I didn't want to point any figures because I wasn't.
No, I do want to point that out, that,
Okay, no, that's
that
fine.
we're not listed.
No,
Okay.
sorry.
So we've talked a little bit about water. How might silver iodide react in soil? Or does it build up and accumulate in soil? Is that a concern?
That is not a concern. I know Klein et al. In 1979 looked at the effect of silver iodide in soil, and it's built up, and there was no effect there either.
Okay.
And you guys can help me out, but I do not, I mean, there was another study or two that had come since that there was no, one of those independent studies that was done, I think it was in Cardo, had done a study where they looked at the soil, or somebody recently had done it was Cardinal.
Cardinal,
Yeah.
excuse me. Yeah, they looked at the geochemistry and the kind of the fate of silver iodide in the environment. It's, again, it's an insoluble compound. Part of the reason that it's burned in a propane flame, it takes a lot of energy to free it up. So when it winds up in the soil, it's inert. It's just another
Right.
particle there.
Okay. Just wanted to make sure I understood all of those. Thank you very much.
Yeah, thank you.
Thank you, April. Okay, just want to see how we were doing on time. We're right on time. Are we finished with this?
Well,
presentation? That was it.
We're pretty much done. I could do later talks, later on. I think we know in social and economic benefits. I'll just leave it there, and that was pretty much the end of my talk, except to talk about future cloud seeding. But I don't think that's necessary here. We can move on if we need to get the crunch.
Okay, DK, that's your
Great.
call.
Yes, we can come back and really appreciate the participation and encourage more as we go forward. But to stay on time, I'd like to thank Tom.
Thank you.
Thank you. Thanks for coming. Thanks for making the effort.
Yeah, thanks for my team. Yeah, these guys are great.
And we're going to shift gears while staying in the same topic. But I'd like to introduce another expert from the National Center for Atmospheric Research based in Boulder, and that's Sarah Sarah Tessendorf. Sarah is a project scientist at NCAR, National Center for Atmospheric Research. She is a project manager for projects that include cloud microphysics, and she'll tell us what that is, and modeling that improve aircraft icing, diagnostic, and forecast products, winter orographic cloud seeding research, and that's really why we're here today, and she'll, I think, focus on that. She was instrumental, I would say, in a recent 10-year study in Wyoming, and I think she's going to touch on that, as well as another study in Idaho. These are both fascinating studies that really, for the first time, quantify some of the benefits for wintertime cloud seeding and in a measurable way. They do this using Doppler radar, in situ aircraft observations, and models. She has published 21 peer-reviewed journal articles, numerous conference papers, presentations like this today, and she's the lead author on a very important bulletin, which I think she can show the crowd and pass out. We have a few copies. That's part of the American Meteorological Society that summarizes the project in Idaho called SNOWY that we're going to hear about. So without further ado, please welcome Sarah, and I'll get her slides going.
Thanks for coming.
My pleasure. It's a nice time to come out to this side of the stage.
Let's make sure your mic's on.
Thanks. All right. Well, good afternoon. I am here from the National Center for Atmospheric Research. As Dave explained, I put my colleague Roy Rasmussen's name up here because he was hoping to come as well, but given the time, the postponement, he wasn't able to join me. But Roy and I, we have a great team of people that work with us at NCAR on this research. We've been doing research to design, optimize, and evaluate cloud seeding programs for over 10 years now, and so I'll give you a little taste of some of what we've been doing. I'm going to first discuss the recent advances in our research that we've been fortunate enough to make, specifically from the Snowy Field Program, where we directly observed the impacts of cloud seeding, and also from our computer modeling. We've been making a lot of advances in computer modeling that are allowing us to study the impacts of cloud seeding in a new way that wasn't possible several decades ago. And then I'm going to wrap it up with some of the research that we've been doing that allows for program design for new programs that are interested in pursuing cloud seeding, ways that we can use our research to optimize any existing programs, as well as the evaluation of any type of cloud seeding program, because in the end, that's what everybody wants to know is, how is it working? So I wanted to start off with this photo. This is, really where cloud seeding kind of began. Back in the 40s, Schaefer and colleagues, started testing the ideas of putting in ice nucleating particles. In this case, in the photo, it was dry ice, but we'll be talking mostly about silver iodide today, into the cloud to see if it could help kickstart precipitation formation processes. Similar to what Tom mentioned, like a lot of clouds, if they form supercooled liquid, they can hang out there that way for a long period of time. But once you get the ice formation, it really helps speed up the precipitation formation process. So in this example, they had this really uniform cloud deck. They dropped dry ice in a racetrack pattern, and lo and behold, you can visually see the impact that it had on the clouds. It created precipitation out of those clouds. Now, the challenge, though, over all these decades has been to really detect that signal, especially because most clouds are not uniform in nature. They evolve over time and spatially, and so to really detect the effect that we're having has been quite challenging, and there have been numerous experiments that come close to finding answers and give us our best guesses to date, but none of them have really been statistically significant at a very high level where the result is not by chance. We feel very confident that the result is not by chance. So this is where our work over the past decade has come in to really try to take new advances in computer modeling, new observations and instrumentation, and new techniques to see if we can advance the field. So this led us into Idaho, just north of Boise. We were there conducting the SNOWY field program in early 2017. SNOWY is an acronym. Like many of us, we work in worlds full of acronyms, but we particularly like this one because it was an appropriate acronym because it was a very snowy winter that particular year. SNOWY stands for the Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment. We conducted SNOWY in order to collect data to document the impact of cloud seeding on precipitation formation, as well as to evaluate and improve some of our new computer modeling tools that we're using to simulate cloud seeding. We deployed a lot of instruments to the Payette Basin north of Boise. The Payette Basin here in this map is outlined in the thick gray line. And the instruments included radiometers to measure the liquid water in the atmosphere, Raywin-sons for measuring the thermodynamic profiles, lots of snow gauges, and other instruments. And this was a real great team effort, a public-private partnership, in fact. The National Science Foundation paid for a lot of the facilities that we put into the Snowy Field campaign, and then Idaho Power also put forth a lot of resources in order to make this campaign a success. We also brought in several folks from universities to participate in this as well. So a couple of the key things that the National Science Foundation provided were a research aircraft from the University of Wyoming. This was the University of Wyoming King Air. It was equipped with cloud physics probes under its wings that could measure the sizes of the drops and the numbers of the cloud drops and the sizes and numbers of the ice crystals in the clouds. It also had a vertically and downward pointing W-band cloud radar, so it could really get some nice detailed measurements of the clouds that they were flying through. We also had 2 Doppler on wheels, or DOW radars, that were positioned atop the mountain ridges to the west on the upwind slope of the Payette. You can see the black cross symbols there indicating where those 2 radars were positioned. And they were really key because in mountainous terrain, as you're all familiar, the NEXRAD operational radars are often blocked, and you can't really see all of the clouds and precipitation that's forming. So putting these radars out atop the mountain, we could get detailed measurements in the Payette in an area that's not always fully visible by the NEXRAD in Boise. In addition, all of the seeding instrumentation was provided and funded by the Idaho Power Company through their operational cloud seeding program. They have a network of ground-based generators in the region, as indicated by the yellow triangles on the map. And they contract with Weather Modification International, or WMI, to do airborne cloud seeding as well. And in this particular program, we had WMI seeding aircraft that could seed with burn-in-place flares on the back of the wings, which are shown in the picture there. These produce a continuous line of silver iodide, from the aircraft. This aircraft also had an ejectable flare capability where it would eject silver iodide flares from underneath the aircraft, and also had in situ measurement probes as shown in the upper left photograph as well. So we were able to measure the cloud drop, number concentrations, and sizes where they were doing the seeding as well during this campaign. So as I go on, airborne seeding was a focus of the SNOWY research. We did do some measurements from ground-based seeding, but the airborne seeding became the focus, and you'll see why in a few slides. Before I go any further, though, with the specifics from SNOWY, I wanted to introduce you to the modeling capabilities that we've developed at NCAR. My colleague Lulin Shui, who's an excellent microphysics modeler, developed this microphysics parameterization in the weather research and forecasting model that we developed at NCAR. And what it does is it simulates the physics of cloud seeding. So you can put silver iodide particles in the model, and they act as an ice nucleating particle that then forms ice and then grows to snow if it's in the right conditions for doing so. So this animation is showing you two mountain ranges where the white contours are the liquid supercooled cloud water just kind of hanging out over the mountain ranges. And then in the simulation, you'll see this cyan color that's showing up now. That's the model where we put some silver iodide into it. Then as that silver iodide encounters the supercooled liquid water, it nucleates ice, which shows up briefly as yellow contours embedded within the cyan color there. So it's silver iodide encountering the supercooled liquid, nucleating ice, and then it forms precipitation, which are the green colors. So you can see here as it goes through again, the green falling out below. That's the simulation of precipitation and snowfall from the model that originated from the silver iodide in the model. You also see lots of green elsewhere too, because the model will still simulate the natural precipitation formation. But what we can do with the model then is we can run a simulation like this with silver iodide in it and look at how much precipitation is formed. We can run a companion simulation without silver iodide and look at how much precipitation is formed, and we can compare the two. So we can quantify where, spatially, and how much additional precipitation is formed through silver iodide. However, it is just a model, okay? And models are not perfect yet. Otherwise, we wouldn't have forecast delays and things like that, right?
Right.
So it's really important that we, one, have good observations to constrain our model and try to improve our model. And that's one of the reasons we went into the field for SNOWY, to get those detailed measurements. And there's other techniques that I'll describe in a little bit later that we can use to also try to account for uncertainties in the model. However, the development of this model is what helped us create our hypothesis for SNOWY. So in this example here now, on the left, let's just start looking at that. We've got a mountain range with a black straight line being an aircraft seeding track. And you can imagine the aircraft going back and forth on this seeding track using those burn-in-place flares, creating this zigzag pattern as that silver iodide advects and disperses downwind over the mountain. In a vertical cross-section, which is taken in this example through the red dashed line, on the top panel, you can see the mountain there at the bottom. You can see in black contours where the supercooled liquid is. Let me see if I can get the pointer to work. Here we go. So here's our mountain. Here's all of our supercooled liquid water hanging out in this case. And then the color contours are going to be the silver iodide. So here's that first line coming through, interacting, depleting the supercooled liquid. And then down here, it's showing the change in ice and snow in the model. So where we're depleting that supercooled liquid, we're producing ice and snow, which then falls to the ground. So this is another look at how the model is working. But the key here is that the model, when you, or in reality too, we were thinking when you simulate or when you seed with an aircraft, you create this really unambiguous zigzag pattern. That doesn't happen in nature. You can get linear features that move through sometimes, but zigzag back and forth, just doesn't really happen in nature. So we put forward a hypothesis that if we seed with an aircraft, you can anticipate this zigzag dispersion where then if we fly our research aircraft, which here is the blue line, research aircraft back and forth, you would be flying in and out of this seeding plume and thereby be able to take measurements inside the seeding lines and outside of the seeding lines to detect and quantify the impact. So this is an example here where the seeding track would be north-south under westerly winds. And then here in the vertical cross-section, it would look like kind of like the animation I just showed where you have these individual plumes that we would fly through with the aircraft and that would fall to the ground. And we would be able to measure these with the Dow radar that's sitting on top of the upwind mountain, as well as with the upward and downward pointing cloud radar on the aircraft, and use those probes that are on the wingtips to get measurements of the drop numbers and sizes and so forth. So that's what we went into the field with SNOWY hoping to achieve. So what did we achieve, I guess? So let me walk you through an animation of this is going to be a radar reflectivity image from one of our Dow radars at the Packard John location. In this particular case, the winds were from the southwest, so the seeding aircraft was flying back and forth along this yellow track here. In fact, as I go through this animation, you'll see the orange dot is the location of the seeding aircraft throughout this animation. So what we see at the beginning of this animation here is there's really not much natural precipitation out there. It's a pretty calm field at this time. And I'm going to walk you through it. Does anybody see anything interesting? So let me go back to a couple key times here where lo and behold, that looks like an awfully noticeable zigzag pattern. And at this time, our seeding aircraft was actually just finishing seeding and getting ready to return to Boise. And so you can imagine that seeding silver iodide advecting downwind, interacting with the supercooled cloud that was occurring on this day, creating precipitation in this zigzag pattern that was readily observable to our eye. And beyond that, let me step forward to this time here. We did have a few seeding legs where we only seeded with ejectable flares. And what's more, you can see the individual dotted pattern in that seeding line that corresponded to an ejectable flare being released every 30 seconds as opposed to that continuous burn in place. So this was a spectacular case. This was beyond what we were hoping to achieve, to be able to detect this so clearly with radar. And of course, we're flying the research aircraft back and forth perpendicular to this in and out of the seeding lines to try to detect what's happening in the actual seeding lines. So let me just skip forward here again. Oops. Nope. So, first of all, a huge success of this program was that we did observe these unambiguous zigzag patterns in the radar, and we got in situ measurements in and out of these seeding lines. But beyond that, we didn't just get this in one case. We actually have it in at least 3 cases where there were very distinct seeding lines that when we advected the silver iodide from the model and some calculations, it lined up exactly with where we were seeing these features on radar. In this top example here, we seeded a north and a south, and you can see the the north one and then the south seeding line coming back down. In this case here, we actually had 2 distinct seeding lines that showed up, and this blue line is corresponding to the research aircraft flying through them. And so you can see what they look like then from the W-band cloud radar, which is looking upward and downward from that research aircraft, which that aircraft is flying along at this flight level, which is the dashed line. You can see here these reflectivity echoes corresponding to that ice and snow being produced from the seeding lines. At the rest of the flight level, this aircraft here was flying generally around cloud top in this case. It was all liquid, and we have measurements on board that tell us how much liquid versus how much ice water content there was. So at this whole time period of the flight, it was all liquid, but when it went right through these, it was mostly snow. Most of the liquid in this had been depleted by the snow formation process. And we have imaging probes that show us what the crystals and particles look like as well. So we can see that these were dendrite type habits of ice and snow forming in these clouds. So again, a huge success to be able to, for us to very clearly in multiple cases detect the seeding impact and then be able to collect that data set inside those seeding lines to detect what was going on. So what does SNOWY tell us, just to kind of wrap up the snowy part of this? Well, one, cloud seeding with silver iodide in the right conditions does produce ice and snow in these clouds with supercooled liquid water. That's one of the big results, and we had a paper come out right away after this project to document that. But moreover, the data that we collected is really just this great data set, unprecedented data set, that is going to allow us to validate and improve our cloud seeding model. And this is important because there are many ways that we can use the cloud seeding model that are of great benefit to cloud seeding programs. And that includes new program design, optimization studies, and the ability to evaluate where and how much extra precip might have fallen from the cloud seeding. So before I go on to the next half of my talk, I wanted to stop and take any questions about SNOWY, because I might mention SNOWY a few more times, but this was kind of the key wrapper about SNOWY. I have a few papers that one of our key papers, I have like 5 copies printed out. It's available because it's in the AMS bulletin journal, but if anybody wants a copy, I can share that too. I guess, is it to come up to the mic for questions?
There's a mute. You make sure the mute's off.
Hey, I'm John Katzenberger. Great experiment that you ran. It's really impressive. I'm curious, were there times when you flew the aircraft and you didn't get the precipitation? It's like, what's the percentage of when you thought it worth it to fly the airplane that you got precipitation that was significant as compared to times you seeded but didn't?
So that is a key question, and I don't have an answer yet, but that is one of the most important parts of the next step of our analysis, is we have these cases where we very clearly saw the effect. There are many other cases where there was a lot of natural precipitation occurring already, and so to detect that zigzag effect is much more challenging, but we have some new ideas on the table that we're starting to pursue in order to try to do that. And in order to do that right, we have to really understand what are those right conditions. So yeah, I don't have the exact answer right now because that's really part of the research. But with this data set, especially with these first 3 cases that we very, very clearly can see the effect, we're really hoping to make great strides on that.
Can I ask a question just about how do we compare the efficacy of using the airplane-based cloud seeding to what we're proposing to do here?
For ground-based seeding?
Ground-based systems. What can you take away from this that we could use
Sure.
to inform us?
So before we did SNOWY, there was actually a program called ASCII, and I don't remember the exact acronym. It's like AGI Seeding Cloud Impact Investigation. Was that, do you know? I might have gotten it, okay. It was in partnership with the Wyoming pilot program, and it was partially funded by NSF and had Dow radars and had the research, it had a lot of the same equipment, but it was a ground-based seeding program. And so the challenges of detecting that unambiguous signal was what made it. I mean, there were some, I think you cited a paper that came out of ASCII, the Jing et al. Study came out of ASCII. There were some great information there, but when you release from the ground, the plume is at the whims of the mountain and complex terrain flow, right? So we can't clearly see that difference. This is where we hope the model will really be helpful, because if we can make sure that the model has the physics right, if we're simulating the right amount of silver iodide activation to ice and the way that the ice forms snow right, then we hope to use the model in a lot of other scenarios where we can't clearly see that signal. Just like the other SNOWY cases that I mentioned where there was a lot of natural precipitation happening, we can't clearly see the zigzag as like we did in some of these cases, but we know there's got to be some effects in there. We're hoping to be able to detect that with statistical methods and with the model. So I think that, yeah, ground-based seeding is more challenging to detect visually just because the mountains have very complex flow, and to be able to resolve those flows in the model accurately is one of the challenges that we need to be able to overcome with the model, but I think the model is going to be one of the great ways to do that. Do you have a comment? I see you going for the mic.
Yeah, I'll add a small amount to that. So, I mean, that is a question that we have as an operator, but also going back to some of Tom's comments, we've used trace chemistry to figure out, are we getting silver that's not from a crustal source into the target area from both ground or from aircraft seeding. And that was some of the work that we did early on. I'll just touch on that when my talk's there. But that is another way to get empirical evidence that we are getting additional snow from silver iodide seeding into the target area. Now, quantifying that is still an elusive beast. That's
That's
part
what we
of
hope
we're
the model will be able to
right,
achieve.
exactly.
See another question in the back.
Come on up, please. You could have a seat there or take the mic, whichever you
Just
prefer.
sit. I'm Raquel Flinker. I'm with the engineering department of the city of Aspen. I'm curious, I see you have detected an increase in precipitation with the cloud seeding, but is that still detected in a long term or not? Is it like, do you get precipitation happening before it would happen without cloud seeding?
Yeah, great question. And also one of the key questions that we're aiming to achieve and answer with this research. On individual cases, you know, we can now detect this. This was a huge stride forward in the research. We're hoping with the model and with statistical methods, we can test this over a longer period with some of the operational programs, like working with Idaho Power and others, so that we can use these new research tools to evaluate it over the long term. Because in the end, you know, how much builds up over the winter, how much extra snowpack, and then how much of that makes it into the streams for hydropower or water consumption, you know, whatever the end result is needed for, is still a huge question that we're hoping to answer with this research.
Very cool. And then the other quick question I had is, could you be moving precipitation from one area to another? So let's say if you didn't do cloud seeding, this moisture would move somewhere else and fall somewhere else, and now you're forcing it to another area.
So that goes back to a little bit to the pie charts that we were discussing when Tom was presenting. So in orographic regions, the mountains are this main focal point for where the clouds are going to form. And a lot of times these supercooled clouds, if the air is going up and over and it only forms small cloud droplets, it's going to move over the mountain and evaporate before it ever produces that precipitation. So we're trying to squeeze a little bit more of that out over the mountain so it doesn't evaporate downwind. There is that, you know, in the big pie chart, you know, probably 1% or less, you know, reduction in water vapor in the atmosphere downwind perhaps then. But what we've seen even in some of our modeling studies is that you put the silver iodide in, it can simulate precipitation formation here, and the silver iodide might continue to blow downwind too. And then when it encounters the next supercooled cloud, it might also do some more enhancement. So yeah, we don't have direct observations to verify that, but in theory, the idea is that it actually might produce more downwind in the next cloud as well if the cloud is not producing the most precipitation efficiency it could.
All right. Thank you.
Mm-hmm. Okay. So I mentioned how we want to use the model and these tools that we've been developing, and one of the ways is for program design and optimization. And so where do you begin if you want to start a new program? I think it's a good idea to start with a feasibility study. This helps justify having a seeding program because it helps you determine when to seed, where to seed, how to seed. Those type of key questions need to be determined. And so our modeling tools have been developed and are great tools for designing new programs or optimizing existing programs to help us determine should we be doing ground seeding or airborne seeding, generator placement, where are the best places to put generators and so forth. And so at NCAR over the past 10 years, we've been doing these types of studies with Idaho Power and across the state of Wyoming. So I'll use some of these examples to go forward to illustrate how we're using the model in these ways. So with the state of Wyoming example, there are many mountain ranges in Wyoming that have been reviewed for the purpose of cloud seeding. There have been feasibility studies in the Salt River and Wyoming Range in western Wyoming, up in the Bighorns, Laramie Range, Sierra Madre Medbo. The Sierra Madre Medbo in particular were the focus of the Wyoming Weather Modification Pilot Program, or WWMPP, which we were participating in that program to evaluate the impact of that program, where they ran a statistical analysis over a 6-year period. And after the conclusion of that, they contracted with us to do the program design study. In the Wind River Range, they've been doing operational cloud seeding there for many years now as well with ground-based generators, and we worked with them to conduct a climatology analysis to understand the nature of the clouds that formed in that area. And so we've been working working now in 5 of these 6 mountain ranges, getting very familiar with the types of weather patterns that occur and advising on program design. And just to highlight, the Wind River Range has been doing ground-based operations for several years now. The Sierra Madre Medbo is now just recently in this last year started airborne operations as a result of some of these studies. So what are the key components of a feasibility study? The key things that I want to highlight, the first one being a climatological analysis, understanding the weather patterns, where you might seed, where the hot spots are for seedable conditions, when that occurs, and then how to seed. Should it be ground-based generators or airborne seeding or even different types of seeding? And then once you understand the nature of the case, the weather in the area, developing and testing a program design based upon that climatology analysis, so you can test where to place generators or aircraft tracks. And then the last step is, in the end, you got to understand if it's cost effective. So part of this is then taking that design and understanding and estimating the program costs to run that design, as well as understanding what the benefits would be from that program that you designed. For most projects, it's extra stream flow. It might just be extra snowpack. But either way, through all of this, our modeling tools that we've been developing have been really beneficial in conducting these types of analyses. So with regard to the climatology analysis, our goal here is to determine how often seedable conditions are met. And specifically for the studies in Wyoming, we've been doing winter orographic clouds for silver iodide seeding. There are other types of seeding, like using liquid propane and so forth. But these specific criteria that I'm going to discuss are with regard to silver iodide. And the two most basic criteria are that you need to have a temperature that is conducive to activating those silver iodide to form ice crystals, which is generally between -5 or -6 degrees Celsius and as cold as maybe -18. And then you need to have a supercooled liquid cloud, because then once the ice forms, that's that liquid water source that is depleted at the expense of that liquid to form the ice and snowfall. Now, when you target with a ground-based program, however, there are some additional criteria that should be considered. Ground-based generators are typically fixed assets, so you put them on one slope of the mountain. So you need to understand which slope is going to have the most frequent upslope conditions. So you're going to have to consider the wind direction and where you put your generators. Also, as we discussed earlier, the ground-based generators produce this plume of silver iodide that's at the whim of the flow around the topography. So you need to consider how stable the atmosphere is. You mentioned the inversions that you look for in your program earlier. You don't want your silver iodide to just be capped under an inversion. It needs to be able to get up and over the mountain into that cloud. And so, so that's another criteria that's important to consider when you're placing generators or assessing if a mountain range can be targeted effectively with ground-based generators. So a big challenge for doing this type of analysis in the western U.S. is the lack of data that we need to do this. You know, we want to know what the temperatures are in clouds. We want to know how often the clouds have supercooled liquid water, the stability parameters, winds, all these things. We don't have that great of data over the western U.S. SNOWTEL data is a key source, though, for us, and so a lot of our analysis will rely on the SNOWTEL data, which give us measurements of precipitation and some other measurements at the surface. Some of them will have temperature and wind measurements at the surface. But in order to do this more complete, we've been relying on some high-resolution model simulations that we ran. In particular, we ran one that covered the entire contiguous U.S. It was a 13-year-long simulation period, and so using this, we have a reanalysis of sorts at very high resolution that includes measurements or simulations of temperature, liquid water content, precipitation, winds, and stability, all of those key things that we want to assess in our climatology analysis. But we still also use as many observational sources as we can. So we certainly use the SNOWTEL data. We compare the precipitation observations from SNOWTEL with this long-term model simulation to get a sense for how well the model is representing the precipitation in the mountain areas that we're studying. And if there's any other data available from radiometers or weather balloon soundings, we certainly look at that to compare as well. So then, this is an example from Wyoming. Then over the entire area that we analyzed in Wyoming, we can produce a map just as a starting point of how often seeding conditions are met. And so these maps that I'm showing here are the frequency that temperature and supercooled liquid water criteria were met, those two most basic criteria. The one on the left is for ground seeding, and so we basically did this assessment between 0 and 1 kilometers above ground level, because that's generally the depth of the atmosphere that we expect the silver iodide from a ground-based generator to interact with. And then the map on the right is just looking at a level in the atmosphere where the aircraft might be able to fly. This level will vary depending on the terrain and what minimum safe altitudes you can fly an aircraft in cloud, but in general over the state of Wyoming, between 3 and 4 kilometers mean sea level was where we looked at. The maps don't look that much different because of the fact that in some of the highest terrain, your 0 to 1 kilometer level is basically the same as your aircraft, but it's around the mountains where it can have some subtle differences. But what these maps show is that, well, one, you can see a lot of the main mountain ranges in Wyoming sticking out. So you can see the Wind River Range here, the Salt River Wyoming Range, the Sierra Madre and Medbo, and the Bighorns up here had, you know, you can see those mountain ranges showing higher frequencies of opportunities. The Absarokas and the Tetons and all this up here also really stand out, but they were outside the area that we were assessing for the state of Wyoming. The Bighorns, you'll see, you can see it, but it doesn't have nearly the high frequencies that, that these other mountain ranges have. Just not as much liquid water content, supercooled liquid water content over this range. But another thing you can see, so the Wind River Range, oops, let me go back. The Wind River Range here extends over this whole period, but most of the opportunities are on the western slope. And this was the case for most of the other ranges as well, that the western slope has the most frequent opportunities for cloud seeding in this state. So then we can, you know, dig in a little bit deeper and look at the, why don't my labels aren't on the plot all of a sudden. I swore they were there before. Anyway, so this is November, December, January, February, March, April. Okay, so we're just looking at a seasonality of how frequent, even the numbers on the plot are gone.
Yeah,
What happened?
I don't know. I know they were there, though.
They were. Anyway, so what we're looking at here are each color is a different mountain range. So the 5 mountain ranges that we studied represent a color that would have been labeled up here.
Okay, see if it'll work.
No,
Sorry.
it's just not showing up. Anyway, so you can see this scale here would be the fraction of time in a given month that these seeding conditions would have been met for ground-based seeding. And so what we can see for most of these mountain ranges is that the December, January, February period is where you get the peak in frequency for ground-based seeding opportunities. And the other thing I wanted to point out when we look at this is one of these mountain ranges is not as good as the others. And in this case, it happens to be the Bighorns. I showed it to you on the previous map that it didn't have as much high frequency for supercooled liquid and temperature being met, but this plot actually incorporates wind direction and stability, and the Bighorns have a lot of blocked flow where the air doesn't get up and over the west slope and it goes around the mountain. So the Bighorns, in this case, were not very feasible for ground-based seeding. So once you have, assessed the climatology and you get a sense for where are the good places to seed and how you might want to seed, you can go forward and create some designs. And so this is an example that we did for the Medicine Bow Sierra Madre Range Program Design Study, where we decided, based on the climatology analysis, the west slopes were the best slopes to target, and we put out a whole bunch of groups of possible ground-based generator locations and tested these with the model. And these are color-coded by groups because we ran so many different simulations with different groups to see, are the generators closest to the peak of the mountain the best, or the ones further upwind, and we ran it through lots of different cases to see what kind of an effect they would give us. And so this is the type of benefit of running the model then, is you can explicitly see how the plume from silver iodide disperses and how it interacts. In this particular case, I'll just point out, there's this red group here that was on the east side of the highest terrain in the Sierras, and this group was actually designed there to target the Medbos by being an upwind source at an elevated altitude. So this is an animation of 4 different ground-based generator locations in the Medicine Bow. You can see how the plume evolves over time. Some of the plume goes up and over, some of it funnels through lower terrain off to the north, or some of it even pools in the valley out here in front. So this is the exact type of thing that we can do in each of these cases, is we can see how does that silver iodide interact with that complex terrain flow. And then when we run the seeding simulation like this, we can look at the precipitation from that and compare it to a simulation of precipitation without seeding and create a map like this. This is just a difference map of, you know, how much precipitation fell in the seeded simulation minus how much fell in the simulation without cloud seeding to get a simulated increase in precipitation. And what you can see is that center generator here produced most of the effect. It got up and over the mountain quite good. The one in the south produced some effect, but that one to the north really didn't have much of an effect, and especially the one out here in the valley that mostly pooled in the valley didn't have much of an effect. So again, so the model here can be used to test the program design, as I just showed you, by placing the silver iodide generators or placing an aircraft track out there in several different types of environments, different wind regimes and so forth, to look for the effects. And by doing that, then we can also evaluate the impacts of cloud seeding. So imagine this was a cloud seeding program that had 4 generators out there. We can simulate this is what the anticipated seeding effect would be. But keeping in mind what I said earlier about models and that they're not perfect, they're getting pretty good, but they certainly still have uncertainty in them. And so we have, you know, always strive to compare our model simulations with observations, to compare, to evaluate performance and constrain the model. But another approach that we can use is called ensemble modeling. And here what we do is we run a large number of simulations to create a whole bunch of possible realizations for a given case. So this map here is just showing you all the possible precipitation outcomes from a certain simulation. This is not from our cloud seeding work, but just an illustrative example of how you can get all these different possible outcomes from a model simulation. What do we vary? We might vary the initial forcing data that goes into it a little bit. We might vary some of the physics options, like, you know, how much silver iodide is going to activate, or how much ice nuclei in general is going to activate. Those types of things that areas where we don't have a lot of certainty in, because maybe we don't have well constrained observations, we can vary those and then create this spread of results. We can also take an average of this as well. So the ensemble mean is a common thing to look at to see, of all of this, what's the average condition. But I think the power in this really is creating that spread of likely outcomes so that you get a range of possible outcomes. So we actually did this for the Wyoming pilot project. For that statistical analysis, we ran thousands and thousands of simulations, seeding simulations, to look at what the ensemble mean effect would be, as well as what the spread would be. So in this example here, I'm just showing a map of the ensemble mean natural precipitation over one of the winters of the program versus the ensemble mean simulated seeding effect, showing you where the enhancement in precipitation occurred and how much extra precipitation fell in the Sierra Madre and Medbo. And what we did then is that we combined this. Literally, it was 9,000 or close to 9,000 simulations that we ran. We replicated the statistical experiment that was done, which had 118 randomized cases. We replicated that by simulating each of those 72 times with multiple variations. And in doing this, we created a spread, and I'll just focus your attention here on the GLEs and the Highway 47 were the 2 gauge sites that were the target gauge sites for the statistical experiment, and then the both column here is just showing the average of the 2. And this is a box plot, and the box in the middle shows you the 25th to 75th percentile of the distribution of results. And you can see that this gives us a range of 3 to 7%. And that percentage is relative to precipitation that would have fallen from seedable storms over the whole winter. But that gives us a range of what the likely outcome was from the cloud seeding statistical experiment. Not a single number, not an exact result, but it gives us a range. And we feel fairly confident that the right answer is somewhere within that range.
Question?
Sure.
This, I think, gets back to one of the other questions, but Do you know what percentage of the actual storms were seedable? Just thinking about kind of the overall impact on snowpack.
And that's exactly what we try to determine from the climatology analysis. In this program, the climatology study that was based on the criteria for the research program, which was a little bit more stringent than what a typical operational program uses. For example, temperatures had to be colder than -8 degrees Celsius, right? And a typical operational program will seed at -5 or -6. So not as often, it was a more constrained time, but it was about a third of the storms in the given winter met the seeding criteria for this statistical research experiment.
Thank you.
Oh, another question?
Yeah, in that statistic, it's 3 to 7% increase relative to just the seedable storms, so it's not 3 to 7% for the precipitation through the winter.
That's right.
And what would that be?
About a third of this.
About a third.
Yeah, because
That
only
would be
about a
the-
third of them were seedable according to the climatology analysis.
So it'd be like 1 to 2%.
Yeah. Mm-hmm. Yeah, it's not the biggest numbers that everybody always hopes for, but this is what we found, and we're feeling like it's a pretty realistic range. But as I mentioned, the seeding criteria for this case or for the statistical experiment were much more strict compared to a typical operational program. And so we do feel like there were more opportunities for seeding that could have been undertaken that weren't in this case as well. But yeah, for everybody in the room, I always caution you, if you see a percentage increase from seeding, always try to figure out what it's relative to. We have to be very careful in how we define what this percentage is relative to, because I think the most meaningful one is relative to the entire amount of precip or snowpack that builds up all winter. But the way that a statistical experiment like this is designed is it's testing it relative to its control counterpart, which is only relative to a seedable storm. So to just wrap up, a quick slide on why are we using computer modeling for cloud seeding. First of all, computer power nowadays is quite sufficient to run large numbers of simulations, for example, like the 9,000 simulation ensemble that we did for the Wyoming pilot study, as well as to run them at very high resolution, so very small grid spacing. And that is critical for modeling complex terrain flows and precipitation in the mountains in particular. In fact, I'll show on this example here, on the left panel is a model that was run with a grid spacing of 36 kilometers versus in the middle a 2-kilometer grid spacing. You can see quite differently how the precipitation is represented, and that compared to SNOWTEL observations, the 2-kilometer high resolution is actually quite good spatially and in magnitude in representing the observed conditions. We're actually at a point now where we can compare with observations within 10% of the observations, and that's within the error of the observations themselves. We're finding that sometimes these high resolution model simulations reveal precipitation patterns that aren't observable in the obs because SNOWTEL sites aren't everywhere. And so even, in some of the mountain ranges I've been studying, I find patterns that I didn't know would have existed because there's no SNOWTEL observation there. And so we've been putting out snow gauges to verify, and I'm quite surprised to find that the model is highlighting some interesting features that we didn't know about. So the fact that the computer models can now simulate the observed precipitation in the mountains really well, thanks to this increase in computer power and thanks to new sophisticated physics parameterizations, that's one key reason that motivated moving to more of a computer modeling approach. And then, as I showed, it's a great way to test multiple design configurations. The world is your oyster. You can put, 100 generators out. You can test them one at a time. You can move them around wherever you want and see what happens. And so it really helps inform program design. And then it provides a controlled experiment for evaluating the impacts of cloud seeding. One of the long-held challenges is once you seed a cloud, you'll never know what it would have done otherwise. And because there's so much natural variability, teasing out a small signal among that natural variability is challenging. And so with the model, we can create a controlled experiment, but it's with a model, right? So it's, there's pros and cons, so I think the combination of using models with physical observations is key. And so I'll just point out that we do, as every chance we get, try to validate and compare the model with observations. Critical observations include snow gauge data, sounding data so that we can make sure that we're getting the right thermodynamic profile. Radiometer data is really valuable but quite scarce because they're expensive instruments, but that tells us how much liquid water is in the atmosphere. In the Wyoming program and SNOWY, we had an AGI ice nucleus counter that we also have used to see how much of the ice AGI particles are advecting downwind to the counter. But in general, now we have the SNOWY data. So we have that in situ aircraft data and the radar data. So we have a whole new data set to go about validating and constraining the model. So in summary, SNOWY collected an unprecedented data set that is allowing us to study cloud seeding in a new way. Specifically, the direct observations of the impacts of cloud seeding were really valuable and a huge success for the program. Also, the advances in instrumentation that allowed us to get some of those measurements in SNOWY and the advances in computer modeling are really paving the way for new progress in the field. Specifically, the high-resolution models providing that valuable insight on precipitation patterns and seeding opportunities. That's really important for program design because I want to point out not every mountain range is the same, as we saw in the state of Wyoming, for example. That Bighorn range just didn't behave like the others. So it's really important to do your homework and figure out, how seedable is my mountain range. And so in general, these advances in the computer modeling and instrumentation are really providing us new tools that will hopefully allow us to study the impact of cloud seeding and make great strides in this research. So I have a few papers up here that are some of our recent papers from the SNOWY project and from the Wyoming Weather Modification Pilot Project. I have, like I said, a handful of copies of the BAMS paper and a handful of copies of the Rasmussen paper, which has that statistical analysis and ensemble modeling evaluation from Wyoming, but they're also available through the journals online. So I'll take any other questions if we have time.
Thank you. We did get one submitted online from our friend, Dr. Jeffrey Deems, who's out of Boulder with the National Center for Ice and Snow. He was, I think, curious about the sensitivity of the radar that you showed for the SNOWY. Mm-hmm. What would happen on a clear day? Would it still detect some silver iodide, or would it be invisible to the radar?
Yeah, the silver iodide is not directly detectable. It's very, very small. The Doppler on wheels Dow radar is a precipitation radar, so it's not going to see even the smallest cloud particles. It's only going to start to see the ice once it forms large enough sizes to be precipitation. The cloud radar is a W-band radar that's on the aircraft that looks up and down. It can detect the cloud droplets, but again, the cloud droplets are still an order of magnitude larger than the silver iodide particles. So those are not being directly measured. We're measuring the ice and the snow that's forming from them.
Do we have any other questions for Sarah before we move on? Looks like we have one.
Hi, Sarah. I'm Andy Mueller. I work with Dave at the River District. And we're in the water supply business and, really look at water from an acre-foot perspective in our reservoirs and our rivers. Can you talk a little bit more about how we verify how much of that snow water equivalent actually makes it into the stream and downstream out of our state or to our water users?
Good question, and I'm glad you mentioned that because I didn't get to that. I didn't have enough time to talk about that in too much, but we are working now with some of our hydrologist colleagues at NCAR. They have developed a hydrologic model that runs driven by the WRF model output. And so what we're doing now is we're taking these seeding simulations that give us a spatially distributed amount of estimated change in precipitation, and we're using that to then drive the WRF hydro, the hydrological model, to try to then assess how much of it's making it into the streams. I don't have the answer for that yet because that's work that we're still doing, but that's one new way that we're trying to use these new tools in order to get a better estimate of how much is making it into the streams.
Thank you.
So thank you very much, Sarah. That was a fantastic presentation. And we're lucky to have for our next speaker, Dr. Sean Parkinson, who has been working closely with Sarah and I think he's going to take some of the theoretical, so to speak, modeling information and talk about how it affects his program at Idaho Power Company as a real resource. And I'll just give you a few details about Sean. I got to know Sean here within the last year, and quite impressed with not only Dr. Parkinson as a leader in his river engineering and atmospheric science group at IPC, but as a skier. And we got to ski and go out and look at some of the sites and some of the targets here in Aspen and in Vail, where they're also doing quite a bit of seeding, as you may all know. But why is Idaho Power interested in this? I'm sure Sean will talk about it, but essentially they are both a water utility and a power utility. And so they're very interested in how to optimize those resources. And Sean's been active since 2003, producing weather products relating to these resources. And really, I've been there since the initiation of some of these key programs and the growth and expansion of cloud seeding in Idaho. And I think it's a potential model for us here in Colorado. How did he build the program? What's going on? What did he learn? So I'm very excited to have Sean here with us today. He received his PhD in civil engineering from the University of Idaho in 2007. And he not only looks at, or at that time was looking at things like geomorphology and its effect on the biology. So he has a very diverse portfolio, and I look forward to your remarks here today. Sean, I'll get your slides up.
Keep track who's driving. All right, thanks for the introduction, DK. So wanted to give you a quick overview of what I was going to cover in my talk today. If you have questions along the way, by all means, jump in. Wanted to start with an overview of Idaho Power. That'll sort of set the stage of why we're interested in water. History of cloud seeding at Idaho Power. Some of the research efforts and application to an operational program. As Sarah mentioned, I mean, we are an operational program. We had a big study done on our operational program. We're not a research entity. We're interested in what do we get out of the whole deal. Then we'll jump into our cloud seeding projects. We'll look at the equipment, target areas, and then touch on the benefits that we're thinking that we're getting from these cloud seeding efforts. So this is a map of Idaho. The yellow that is, if I can get the... Do
you want the pointer back up?
Pointer, yeah, if I could. So the blue line across the southern part of the state there is the Snake River. The yellow highlighted areas, that's our service area. So our service area goes from the Pocatello area along the Snake River over into eastern Oregon here, and then we've got a little sliver up here along the Montana border, of which Salmon is part of. We're an investor-owned company. We have about 560,000 customers. Our service area is about 24,000 square miles, about 2,000 employees, and we've got 17 hydro projects there along the Snake River or within the Snake Basin. 13 of those are on the main stem snake itself. So this slide here, so we're an electric utility. This pie chart here shows, or this donut chart, shows the energy mix in 2018. And 46% was from hydropower. About 19% came from other purchases, long-term purchases. So long-term purchases are small hydro. There's a little bit of nuclear. There's some fuel, but there's also some wind and solar in there. And then we've got coal and some natural gas. But the take-home here is we're a hydro company. There aren't really any other private utilities in the country that get that much of their generation from hydro. There's a number of utilities that get some from hydro, typically in the 5 to 10 or 15% range. So water is really a key thing for us, and that's our cheapest generation resource. So that's really where the rubber hits the road. Why are we interested in this? When I started a number of years ago at Idaho Power, this number used to be in the 65 to 75% range. Some change in stream flows and then change in load are what has changed that mix. So as I go through the talk here today, this is again southern Idaho here, and then this more or less yellow outlined area with some green here. That's the Snake Basin above the confluence with the Payette River here. We've got the Payette watershed. That's where we had our first cloud seeding project. And there's the adjoining Boise and Wood River basins, and then the Upper Snake. And then the little dots here along the Snake River proper, those are where our hydro facilities are. These three down here make up the Hells Canyon complex. The Hells Canyon reach of the Snake River starts here and goes north to Lewiston. About half of our hydro generation comes from these three here, so downstream of all of our cloud seeding activities. So I'll step through the history of cloud seeding and how it's grown from a question to a fairly extensive program now. Back in the early 90s, I started there in 1990, and I worked on forecasting stream flows. And I was also looking at how salmon recovery efforts in the Northwest might affect upstream reservoir operations and then stream flows and the timing of those flows that would affect our hydro generation mix and when we would see that. There was a pretty severe drought in the Northwest that started in '87, and about 1992, there was getting to be a fair amount of consternation and concern about we've had continuing low stream flows. That's driving power supply costs up. We have a bunch of share owners that are pretty interested in returns, and we were spending more money on buying power and burning coal and not using our hydro. So lo and behold, a share owner asked a question in '93 about why weren't we at least investigating and applying cloud seeding to maybe mitigate the effects of the drought on our hydro system. So we embarked on a investigation, call it a feasibility study, to evaluate cloud seeding's applicability in the Snake Basin. The take-home message of that effort was that cloud seeding likely was a viable long-term water management tool in the Snake Basin. Long-term, I think, is a key take-home here. It's really not a drought-busting mechanism. Our literature assessment and some of our preliminary modeling showed that it's probably not going to have the ability, we're not going to have the storms in those dry years to have an overwhelming effect. But in the Snake, there's a fair amount of storage. So doing cloud seeding persistently over a long period of time, increasing base flows, reservoir carryover, it was likely going to have a long-term beneficial effect for us. You'll see quite a gap here from when we started that feasibility study to when we went operational in 2003. That really wasn't because we had a hard time getting our head wrapped around whether it was a viable water management activity for us. That was a lot about working through electric utility deregulation. Were we going to be an integrated utility? Were we going to be anything at all? Who pays for it? Who gets the benefit? So it was really a funding and benefit question that we had to work through with our Public Utilities Commission. We went operational in the fall of 2003 with a fairly small program. We had 7 remote operated ground generators, an aircraft, and an assessment. And I'll go into a little more detail here than I typically do. The PUC, they wanted to see that we were actually putting silver where we wanted to put silver. We were hitting the target area. So we had 7 generator sites, but we had co-located generators there, and one released silver iodide, one released indium. So we had a tracer so we could tell whether the silver at that site was coming from a cloud seeding generator or not. The aircraft, we were releasing a tag cesium silver iodide solution so we could tell silver in the snowpack, was it coming from ground or air or a crustal source. So we were able to drill into that ground, air, or other source question. That effort lasted a couple years. We wrapped that up in 2005 as far as the assessment. In that time frame, moving forward to 2008, there were a number of other water resource concerns brewing in the state. The Eastern Snake Plain Aquifer is in the upper part of the Snake Basin, up in here, and there's about a million acres of irrigated ag from groundwater in that region. You might imagine that that's taking a fair amount of water out of that Eastern Snake Plain Aquifer, which was having effects on surface water resources, and we had a battle brewing between surface water and groundwater users. The governor decided to get everybody in the room, knock a few heads together and say, figure it out, come up with some mitigation. We had a seat at the table in that room. One of the things that came out of that effort was to look at cloud seeding as a means to get more water in the Upper Snake, not necessarily to address the water right issues, but to give a little relief and some time to sort out some longer term solutions as far as other water conservation efforts or fallowing, aquifer recharge efforts, and cloud seeding was part of the mix to give some more water, to give some time, and basically just put some more water in the system. So in 2008, we started a 5-year pilot program. That was a ground-only effort. We joined an existing cloud seeding effort in the Upper Snake that had 25 manually operated generators. So it's been a collaborative effort since then with that group. In 2009, we started tracking or participating in the Wyoming program. That's where we met NCAR. I met Roy Rasmussen at some meetings there, built a great relationship, met Joe Busto at those meetings, got to know some of the players in some of the other states. That was really a phenomenal place for me to get out of Idaho and figure out what other people were doing and bring home some of the lessons learned that were happening in Wyoming and Colorado and Utah. In 2010, we started working with the Western Wyoming RC&D, building on a feasibility study that was done in the Salt Wyoming Range. Those watersheds are just adjacent to the Snake, and it's like, is there an opportunity to grow into those watersheds? In 2011, we commissioned work with NCAR to develop a WRF application for our Snake Basin and develop a cloud seeding module to go with that. That cloud seeding module, we had envisioned early that it would guide our seeding operations. We'd use that to look at program design, where to put ground equipment, where to put the aircraft, how often would it be usable, how often would that equipment or the releases from those ground generators get trap sand or inversions, would we be bound by canyon flow or whatever. Get past the conjecture and use another tool to figure out how to design the program. That work's still ongoing. That was definitely part of SNOWY. We were starting to get a lot more attention from the water users in the state of Idaho as far as, okay, this thing's not just the Payette Basin anymore. We're getting traction in the Upper Snake. If you remember from the service area, we don't serve customers in the Upper Snake, or very many of them. And so we were sort of the downstream people that wanted water out of the Upper Snake, and we were sort of a thorn in their side. Our efforts with cloud seeding, we actually built some really strong water resource relationships. That was the common theme that we could have when we were talking about some pretty controversial issues. That's something that we were all sharing in. We all saw some mutual benefit. So it was really a good effort there. So in 2013, we had a group of irrigators. They owned the Bigwood Canal Company. They came to us and said, "You're doing cloud seeding in the Payette Basin. Can you use that aircraft to seed our basin when you're not using it in the Payette?" And we did. In 2014, they wanted a ground program. The Boise irrigators came to the table at the same time. They had been using a manual-only program off and on, and basically they saw the value of joining forces with the Wood River irrigators, getting an aircraft to target both of those watersheds, and then sharing ground equipment between the Payette, Boise, and Wood Basin for wider area effect of seeding. So that really kind of filled out that west central mountain or the Payette, Boise, Wood area. We continued to chip away in the Upper Snake. In 2000 and by 2015, we had grown from 7 generators and 1 aircraft. We had 43 remote ground generators and 2 aircraft, along with some other equipment. And then in 16, we had snowy. We added an aircraft to the Upper Snake. And then this past season, we had 57 remote generators and 3 aircraft. We're contemplating adding a 4th aircraft, an additional one in the Upper Snake this coming season. So that's an overview of the history of our program. A little bit more on snowy. I won't review the acronym again. I always get tripped up when I try to do that. Some things that Sarah didn't mention, though, is that the bulk of the funding, she did mention it came from NSF, but it was an appreciable amount of funding. It was $2.1 million to fund research on the Payette Basin, an operational program. And that was sort of an unprecedented level of funding in the U.S. for cloud seeding for a number of years. There hasn't been any appreciable research done in the U.S. for a long time, short of the Wyoming project. And I need to mention that a lot of the ideas for snowy leveraged from the work that was done in Wyoming. It's like, all right, what had they wished that they had been able to accomplish there, and how to do that and make sure that we get some of those questions addressed in the next step. So there was a lot of synergy that was done there. The field campaign was in early 2017, but the work is still continuing. There was a collaborative effort between NCAR, University of Wyoming, UC Boulder, University of Illinois, and then Idaho Power. But our part, we were not an applier or a participant in applying for the funding. We were acknowledged as operating the program. We committed to operate the program. We provided an operational program. We provided a fair amount of field support, getting equipment out in the field, logistics, provided a home base for meetings and an operations center. So there was a fair amount that we brought to the table, but we did not receive any of the $2.1 million of funding, nor did NCAR really, right? I mean, we funded NCAR's participation there. Some additional efforts captured down here that were not part of the NSF funding. We had Boise State University do some trace silver work. So we went out in the field and we sampled the snowpack to see where we were targeting. Weather Modification Inc. provided they provided more research probes, a larger aircraft with research probes on there, and an ion counter in the Payette watershed. So it went a little beyond just this NSF funding itself. I wanted to touch on a couple of other applications that went beyond what Sarah showed, but they've already been mentioned. From a research perspective, and this became particularly relevant when we moved into the Upper Snake, it was like, okay, where are the inversions affecting where we might want to put our ground equipment? And so some work that NCAR helped us with several years ago, we looked at in the West Central Mountains. We released soundings from Crouch, which is in the heart of the Payette target area. So we had a pretty good data set of soundings and when we might have inversions setting up there and where. And then also we've been releasing weather balloons out of Idaho Falls. And I think the take home here is that the elevations in the West Central Mountains where we get inversions setting up are much lower than in the Upper Snake. So going back to one of Sarah's comments, every watershed's different. We need to understand where we're putting our equipment, where we're intending to work, and understand the atmospheric conditions that set up there that might either benefit or potentially impede seeding operations. Another comment that's here is within snowy, they found that the clouds over the Payette didn't really have a connection with the surface all the time. And so again, there might be seeding opportunities aloft, but we might not be able to get seeding material from the ground up to where the liquid water is. We didn't see the liquid water pooling down lower and within the mountains where the silver iodide might be released from ground equipment. So this is the take home here is it's really important to dig in and understand the watershed you're needing to seed and how you might best go about it. Next slide is similar to one that Sarah showed, but this one we were looking at seeding opportunities in the Upper Snake and when and how to use, or how ground equipment might work up there. So this is Craters of the Moon. Here we got the Snake Basin, Snake Plain coming down here. These vectors are showing wind directions, and we've got silver iodide being released from ground generators. And we see some of it coming up and over the Tetons here, but some of it's just settling right down. This is American Falls Reservoir here. Some of it's just settling right down into the Snake Plain. It's not going to do anything for augmenting snowpack. So the take home here is some of these analytical tools and the modeling that are out there, especially with some of the retrospective simulations and that data set that are available. The information's there to look at, where might we be able to put equipment, where might we best seed from, and what the effects might be. This is a snapshot from the Pocatello National Weather Service radar that was captured just this last year. One of the contract meteorologists from WMI was on duty. He was running the one of the aircraft in the Upper Snake out of the Pocatello airport, and he was watching the radar signal, and you can see that zigzag shape showing up here. And so the point of this is we don't have to have a $2 million field campaign to see the effect on radar. But this was the first time that somebody was watching it, that had an eye for it, that actually had the wherewithal to capture it. And it's a pretty intriguing and fairly compelling video clip of, all right, here was an operational effort, it wasn't for research, and we got it. You've seen pictures of this is an Idaho Power remote cloud seeding generator. We build these things for ourselves. We started out buying some years ago from Weather Modification Inc. and trial and tribulation. It was like, you know what, it's time to redo one of these things and fix them so that they work the way that we want to maintain them, and just get them to where they work for us. We retained some of the key components of how the burn chamber works. It's basically goes back to some of the research that was done at Colorado State University in the cloud chamber, so we've preserved that. But by and large, the rest of it, the communication system and how we pressurize it, the modularity of it so that the pieces are plug and play, that's been our deal. And Dave installed a couple of these last year to operate in Colorado, and there's 2 of them up on the Grand Mesa as well that Slade and his group run, and there's a total of 6 of them in Colorado now. And then we use an aircraft. We've got 3 of these at the United King Air. As Sarah pointed out, we've got burn-in-place flares on the trailing edge of the wings. This is a little different shot of the ejectable rack. So having ground, burn in place, and ejectable give us the opportunity to seed a wide range of storm conditions and temperature conditions and where the liquid water's at. I got a hurry up note. All right. So here's a map that shows what our current program looks like. So over here is the West Central Mountains. All of the little crosses are where we have remote ground generators. The gray lines are where we have predetermined or predefined flight tracks for the aircraft. And then the green dots in the Upper Snake are where there are manual generators. The magenta crosses are where there are remote generators, and then the gray lines again are the aircraft track lines. Suspension criteria were mentioned before. This is something that we watch on a pretty regular basis, particularly whenever we're getting close to those thresholds. The red lines indicate what the suspension criteria are by date. The blue line is the long-term NRCS average, and then the green line is the observed SWEA in each of these basins. You can see here that we got close in the Boise. We didn't touch it for SWEA. In the Wood, we did cross it in both regions that we watched there. So we did suspend in the Wood River Basin for snow water equivalent this past season. We also monitor search and rescue, avalanche concerns. We suspended on these days that are noted over here. And then we also watch SWASI. We had a scenario several years ago where the reservoirs had a significant amount of carryover, so they were full, and we had a very modest snowpack. But we were set up for a flood situation just because of the reservoir conditions, and that was a lesson learned there to watch those as well. We watch the SWASI, that's the Surface Water Supply Index that the NRCS publishes, and it's the combination of storage in both snowpack and reservoirs. So I just wanted to share that suspension's a real thing. We do watch it, and we do have times when we suspend. So the question came up a little bit ago, what do we get out of this? So one of the ways that we watch our benefits is we do a target control analysis. We look at target areas where we're not having an effect on snowpack, or where we are having an effect, and control areas where we're not developing a regression from a period that precedes seeding, and calculate a benefit based on that statistical model. This column here shows the average for the period that we've been seeding, the average percent increase in annual snowpack. The Payette has been a little over 11, the Boise 15, the Wood about 10. The Henry's Fork, that's the northern part of the Upper Snake, about 5, and then the part above Palisades, almost 8. In the interest of time, I'll skip that one. So we take those SWEA increases, put those into a hydrologic model, run those over a period from 1950 to 2003. And we do this for our integrated resource plan. And we look at the difference between a seeded and unseeded hydrologic simulation for that time. And the average increase in runoff in the Payette is a little over 200,000 acre feet. In the Boise, almost 230, and in the Wood, 113. The Upper Snake, 424,000 acre feet. That's an average estimated from our current level of build out. In total, that's almost 1 million acre feet of additional runoff. At build out in those same areas, looking at the additional aircraft and putting some more ground equipment, we think we can approach 1.3 million acre feet. Some things that I've recently started sharing is all right, that's the volume of water. We're an electric company. What does that mean? That's equivalent in 2018. We had a lot of spill in 2018 for a variety of reasons. Some of that was maintenance, and it was a phenomenal water year. That's about 725,000 megawatt hours of energy, even accounting for all that spill and everything. Well, what is that? That's about 57,500 homes. Well, that's a fair-sized community. I mean, that's a city of a couple 100,000 people. In terms of coal, I mean, we operate coal plants. That's over 700,000 tons of CO2 that weren't emitted because we had that hydropower available. In terms of solar, it would take a solar farm of an installed capacity of 317,000 megawatts to accomplish that same level of generation. In wind, that would be over 220 megawatts of nameplate. Anyway, that summarizes what I had. Any questions?
Fantastic. Any questions for Sean? Well, thanks. I really am intrigued by what you've done in Idaho, and I think it's a potential model for us in the Colorado River Basin. And some of the benefits you talked about, I think, would be helpful for us to understand even better as we go forward. We are, well, let's first thank you. We are scheduled for a break, but as facilitator, my prerogative to try to keep us on time is to maybe have, okay. Well, we're going to shorten our break a little bit and try to get back here as soon as we can, 5 minutes, and we're going to let Dan Breed talk, and then we'll have our roundtable and closing. So thank you very much. We'll be right back.
All right, well, I'll go.
All right. Welcome back to the Public Cloud Seeding Workshop here in Aspen, Colorado, Pitkin County. We're in the Pitkin County Commissioner's Room. We have another speaker. I'd like to introduce Dan Breed. Dan comes to us from Boulder, Colorado. And, excuse me, Dan is formerly from the National Center for Atmospheric Research. Dan worked there for 10 years. I'm sorry, let's see.
41.
41 years? 41 years, excuse me. I was looking at your education. He should be Dr. Dan Breed. He did all the PhD work, didn't complete the dissertation in atmospheric science at Colorado State, but obviously has a strong portfolio and a lot of research in cloud microphysics, cloud electrification, cloud dynamics, and radar meteorology. A lot of field experience, of course, and a lot of teaching experience. And Dan's going to talk today about a study that was completed in 2015. Although it's not the most recent study, it's the closest to home. Here it studies this basin in particular, the Central Mountain River Basin, and why and where to seed in Pitkin County. So with that, I'd like to turn it over to Dan.
Thanks, DK. You gave me kind of an optimistic title there, so I'll have to tone it down a little bit because it really is just basically the Central Colorado Mountain River Basin study that, and because Front Range Water Council paid for part of it, it actually concentrates more on even the Winter Park area for some of the case studies. But most of everybody else has talked about lots of stuff that I'm going to go through, so I'll skip through kind of quickly on some of these things. I'll talk briefly about what goals of the studies or the tasks that we had. Seeding criteria, which we've already heard a lot about, but I'll explain that a little bit more for this particular study, and the target area. and then the method that we used, which used something that Sarah had brought up in terms of the 4 kilometer, what's called at the time was called headwater simulations or model simulations. At that time, it was only 8 years of it. It's now 13 or more years. It was a high resolution model, 4 kilometers, so that's the primary data source that we used for the study. So this is kind of the earliest of the evaluation type of studies that were done at NCAR, and kind of done in a poor man's world at the time. And then some results and very briefly some future work. Oops.
There should be a clicker. Try clicking the mouse there.
I did the wrong one there. Yeah,
Gotcha.
There you go. Is this going to work?
Yep.
All right. So the overall study was to look at the effectiveness of what the ground-based seeding generators are doing in the central Colorado mountains, and it was kind of a 2-part study. One was the climatology, which is what I'm going to concentrate on here. The second part was to look at a very high resolution, down to 1 kilometer resolution, model study to look at some of the plume effects from ground-based generators. But that study in particular was concentrated on the Winter Park area, so I'm not going to talk much about that at all. So we've already talked about criteria, and one of them is cloud microphysical properties. The biggest one we need there, of course, is supercooled liquid water, the second part. The existence of a cloud, obviously, is necessary, but again, we're talking about using a model here, and some of the existing data sources like satellite data or even video data, for that matter, in terms of the existence of cloud and cloud coverage, and then supercooled liquid water, which is not typically measured at all. So that's one of the biggest reasons that we're using a model. Radiometer is a instrument that will give an indication of supercooled liquid water, and that's been used for many of these more specific research programs, but that's typically not available. And then again, other things like cloud temperatures, which affect the reason that we have these cloud temperature criteria is because trying to understand ice nucleus concentrations naturally and how effective that might be, and then where silver iodide is most effective, or where natural ice nuclei become effective and silver iodide has no additional effect on them. And of course, in some cases, you also, if it's already precipitating, then that's could be a signal for some of the criteria. And then the other aspect of it is targeting. You got to have where are the clouds? Are they high above the crest or at the crest? What altitude levels? Again, and then wind direction and wind speed for ground-based generators. And again, we've talked about this before, no low-level inversions or stable layers that are going to inhibit the flow of silver iodide into the clouds. And then finally, the last one really, which is really a forecast, and it can be fairly subjective, is a criteria for how long it's going to have. Are these conditions going to last for some time period? If it's something that's only going to last for an hour or 2 hours, that may not be very effective. If it's a major storm, then that's a different story, and then you work with it from there. So a forecast is important too. This I'm not going to go through this one. This basically shows you real quickly at the bottom here a time series plot, and this blue line here is a radiometer showing liquid water content, and the other line here it indicates snow gauge data, and it's just showing that in the top part's a model, so it's just showing in this particular case how the radiometer and models are agreeing, and the resultant kind of precipitation that is falling from this particular case. For the central Colorado mountains, these are the seeding criteria that were used. I'm trying to think if this is, yeah. So this is what was used. A cloud base that was above them, or that was below mountain to crest. In other words, something that sits on top of the mountain or lower. Temperature greater than -5, just below the mountain crest. Winds favorable for targeting, obviously. No inversions or stable layers from the surface to basically to the mountaintop, or -5 level at least. Temperature at 700 millibars, that's not colder than -16, because once it's more natural. I mean, natural precipitation is going to happen at temperatures that cold or colder, for example. And silver iodide, silver iodide doesn't really have a chance to enhance something from a very, very cold cloud system. And again, the forecast factors of winds and precipitation and the duration of the events. And then in 2014, at least, remote operated generators, and there were only 2 of them, and they were in the Winter Park area. They relied on cloud cover that was more than 50% over the target, a temperature at 700 millibars of warmer than, or of -5 or warmer. The occurrence of precipitation was not required, but it was useful. In other words, it was pretty obvious that these, if the other conditions were met, and it's already precipitating, it's a good chance to be good for seeding at that time. And then in that particular case, the wind direction needed to be from the west to northwest to affect the Winter Park ski area. The seeding criteria used for this study, and now I'm trying to apply the criteria to model data, to gridded data, basically. And so you needed a mean temperature. We used over an entire target area. It needed to have a mean temperature at 700 millibars between -5 and -15, and have cloud mixing ratios. In other words, you have some liquid water, and an environmental lapse rate that was somewhat unstable, stable to unstable, meaning things are going to want to go up and flow over mountains. Temperature criteria are grid. Now, we can also do this by individual grid points rather than for a whole target area. I'll get to that in just a second. And that's worse. It's at 600 millibars, partly because if you look at a grid point, lots of times 700 millibars is in the middle of a mountain. It's not, mountains higher than 600 than 700 millibars, for example. So I use 600 millibars to pretty much get it over top of all the terrain. And there, in that case, it's using -16.6 as the warmest at that level. And if or the coldest at that level, and warmer than -26, which would be quite cold. So that would be natural precipitation would be overwhelming any kind of seeding signature. Again, you have to have cloud liquid water or supercooled liquid water, a lapse rate that is unstable or at least neutrally stable. And then at this point, we're also saying that the wind direction needs to be in this west to kind of northerly direction. So we're limiting this based on the location of those two gauges up at Winter Park. Certainly, refinements to future work, and Sarah already mentioned this, is that you need to improve some of, or the matching of some of the thresholds, for example, and even more important, varying direct wind directions and speeds for different kind of generator operations and locations. So that would be something that you'd want to do in general here. You've already seen this one from Eric. The blue outline here is what I call the target area, right in here. This included some of this green and red area as secondary target areas. I guess if you use one, does it not let you use the other, or what?
You can just use the black one. Yep. Yep.
Oh, yeah. So Pitkin County, in this particular, what on the other graphs I'm going to use, is basically down here at the south end. It goes more to the west as well, but at least you're going to see an outline of that blue area, and just keep in mind that it's down there at the south end is where Pitkin County is. So in this big black, in the middle of the red box there, which is the inner domain, you see the target area of that in the south. That southern most part of it is Pitkin County area. You can actually see on this. This is just topographic data. You can actually see. It's 4 kilometers, but you can actually see where Pikes Peak is and Longs Peak, and as well as other prominent mountain ranges. And so this is now resampled down to the smaller scale. You can see the blue this area down here, which is basically Pitkin County area, and the mountain ranges around here. If you click through that, you can see it jump out at you here. On this graph, all the squares are black squares, and they're kind of labeled. They are snowtail sites. The dots are all generator locations. So a method we use is look at this kind of resampled domain, the smaller part of Colorado, and in the target area in particular. And we looked at just 4 of these pressure levels, 750 to 600 millibars, which is about 8,200 feet to 13.5. It's every hour. Time steps are every hour. And the time period we analyzed was from November through April. It was for these 8 seasons that we had data for at the time. This is just an example from one day, and you can see in the upper left, and it's temperature, for example. In the upper left, you see most of it's white. That's because the terrain's blocking most of it. So if the terrain is not at 700, is above 8,200 feet, there's going to be no data there. You can see a little bit, few of the valleys, but that's about it. The next one over on the upper right is at 700 millibars, and so again, there's quite a bit of terrain blockage there. Then the lower left is 650, and the lower right is 600 millibars. And the only thing I wanted to point out there is that this is just one day. It's and that's what the levels are for temperature, and you can just see that there's a kind of a storm coming through from the southwest, and it's colder down to the southwest and gets warmer over the target area. There's a little bit of a gradient, and then way off on the right, I don't know, right about quarter of that or fifth of that is actually over the plains. It's past the mountains. I think I'm going to skip this one. I'll just go to this one. This is 2000 to 2001. I think it's for the whole season. And this is the conditions, or is it just, I can't see that very well. Oh, yeah, it is. And this is a red, this is time series of different values of temperature and liquid water, so forth. Let's see, snow is the middle one, ice particles is the second to bottom, and then the bottom one is precipitation, 1 hour precipitation. So the red is when the seeding criteria is met during that season. What you can see is as you get to April and it gets quite warm, you just get you get those few outbreaks of colder weather that are seedable, and there's a better graph here to point out from year to year what that looks like. But this is for this 1 year. This is what it kind of looks like. The other part of it that's quite interesting is how most of the precipitation periods are during seedable conditions, except as you get closer to end of March and into April. This is the whole 8 years, but it's only for 1 month or 1 week. 1 week over one for the whole 8 seasons, for example. Again, it's similar type of a plot, except where red meets the seeding criteria. So if we can, I'm not going to go through the details of this one, other than the fact again that the second one from the bottom, you can kind of see that there are some pretty significant precipitation events that aren't seedable, but most of them, even smaller ones, tend to be more seedable. So this is a graph very similar to what Sarah had shown. This is over 8 seasons, and it's a percentage of time that seeding conditions were met for the whole target area, which I pointed out earlier what they were. And the lowest, the month with the lowest or fewest is April, because it's warmer, mostly because of that time period. And the highest one is in March or in February, with January and March pretty good too. And this is all of this is a percentage of all time periods. This includes days that are all sunshiny as well. So 20% of the time, on average, over this time period, are seedable conditions in that bigger target area. If we looked at again now, this is looking at it in the grid point, from a grid point representation, and again it's over eight years, and so upper left is the temperature criteria. The upper right is whether you have cloud or not. The lower left is instability criteria, which is pretty flat. Doesn't give you that much detail or isn't that restrictive. And then the other one is the winds, actually. And that one's a little more restrictive because we're just looking at west to northerly winds. whereas around here you might get quite a few things from southwesterly winds. So if we look at this grid point data from the 8 years, and you look at the frequency of seeding criteria for all 4 of those, and you plot them up as one plot, in other words, it shows you kind of hot spots of seeding. So you can see that it follows, it more or less follows mountains as well, but there are areas in that upper left that have a little more nuance to them than just topography. And so there are some areas there, particularly down Pitkin County, how it shapes up down there, that could be kind of interesting. And then again, the snow that actually falls during that time period is in the lower right, and you can see they more or less they follow somewhat the same pattern, except there are some very significant differences, particularly up in the northern part of that domain. So if you normalize it now by whether it snowed there as well as whether you had seeding potential, and then you plotted all the generator locations, and you look at the Pitkin County area there, you can see how this particular study showed kind of hot spots in the area here in terms of seeding potential. So future work is to fine-tune the criteria, obviously. It was kind of our first guess at stuff. Actually, a really good way or better way to do this analysis with GIS. We kind of did it the hard way to begin with. And it's much easier to try different scenarios that way in terms of climatology. And then you need to cover targeting from more generators, so you need to do it with lots more varying winds. And then in fine scale modeling might help with some of the precipitation patterns and wind trajectories if you want to look at particular generator locations, for example. So with that kind of summarized.
Thank you.
Yeah, thank you so much, Dan. Do we have any questions? I mean, it seems obvious to me that study kind of points to Pitkin County as a pretty good place to continue looking, studying, and working on cloud seeding. Obviously, we brought a lot of experts here today. We're looking for now reactions, questions, and input. And to do that, now we've assembled a myriad of folks around the table.
DK, I'd love to bring in my fellow Commissioner George Newman, who's here and has questions prepared. George, come on up.
Stick 'em here.
Come on up and join us. Hey, well, there's a seat and a microphone.
Oh.
I don't know how often you get to sit on that side of the table. It's kind of
scary.
Thanks. I have a couple of comments and questions just to maybe help stimulate the conversation. But first, I really want to thank the River District for organizing this, and all of our guests who've traveled near and far. So thank you all. It's been extremely informative, and a lot of it's certainly over my head, but it's been interesting. You know, from the Pitkin County Board of County Commissioners' point of view, our concerns when this proposal first came to us focused on 2 areas. One was our environmental concerns, and of course, as was stated at the very beginning, you know, Aspen was built as a silver town, and so there were certainly concerns there. And just up the hill here, we have a Superfund site that maybe many of you don't know. So environmental concerns was a key issue, and what I gather today from all the data and the research that has been presented, that should not be a concern of ours, or as which was good to hear. The other concern that we have, and I think has been noted here through a lot of these presentations, is sort of the cost-benefit analysis. looking at this. And what I've seen is a couple things. I think Sarah addressed some of the challenges in terms of the need for more updated data and modeling. The data that Dan just presented is 10 years old. And as we know, with climate change, we have records that April can talk about. In the last 10 or 20 years, we've seen 30 more days of frost-free days here in the county. Our winters are shorter. Our weather is warmer. And when we talk about ground distribution and trying to reach those temperatures, as Dan said, right now, only about 20% of the time is seedable. Sarah talked about in her model that in terms of the potential benefit, if I got this correctly, was 3 to 7% increase relative to the precipitation from seedable storms. Only about a third of those storms are seedable, and so that only leaves us about a 1 to 2% overall benefit, if I followed that correctly.
From the Wyoming study specifically.
From the Wyoming studies, right,
Yes,
thank you.
the
But it's still, it's interesting that in terms of what we would need, in terms of trying to get some more updated data and modeling would certainly help us. The ski company, as was noted, over the course of 2 decades, from the 70s to the 90s, have tried this and experimented, and it'd be interesting to hear Rich's point of view in terms of how they saw the cost and benefit as well. So I think those were some of the questions that the Board of County Commissioners had and probably will still have, and this is great information for us to look at, and hopefully that will sort of start some of your discussions.
Great. Well, thank you, George. I'm not sure exactly how to handle that series of questions. I could take a crack at 1 or 2 of them and then maybe add some, or as you say, keep the ball rolling in a sense. Just 1 or 2 corrections. The study that Dan presented was 2015, so not quite 10 years yet. But and you know we do need site-specific data. We are continuing to refine that. The tools that NCAR presented on today provide that opportunity, I would say, to refine those models. And I think as good stewards that we want to be, putting together a monitoring, assessment, evaluation program should go hand in hand with a program like this. And we are, in fact, doing that. We have similar target control programs that do use statistical analysis to try to get at the gains that we're all looking for in terms of water supply and snowpack. They are in that range, a little bit greater, 3 to 7, maybe 5 to 15%. We publish annual reports on those using those studies for the Central Mountain Program, and again, they're in that range. But you saw the variability. We know year to year those yields, those differences can be quite variable from last year, incredibly dry year with very few seedable storms, to this year where we had, I think, 25, 26 seedable events in the target area. So the thing to keep in mind also is that we're looking at a very large land mass, so a small gain across a large area can have a large volumetric impact, like Sean Parkinson talked about in the Idaho example. So that's some. I think you raised some great points, and we want to continue, I think, the conversation here to address some of those. I don't know if I got them all, but I know we have assembled around the table local managers, emergency managers, recreational managers, climate experts. And so what I guess I would propose is if we can go around and address that and expand upon your series of questions with general reactions to what was heard today, what was presented, and if you have similar concerns that were just expressed on cloud seeding, and if you think cloud seeding might benefit or harm your agency, your mission. And then another thing to just think about as we go around is how do you see cloud seeding in the future? Is it something that is potential hedge against climate change? Can it be a mitigation or adaptation to keep us in business here, whether it's a recreational wintertime activity, recreational summer river activity? There's a whole myriad of issues that come out. Water supply, of course, is where the Colorado River District comes down, and we have been looking at this along with the 7 basin states for the Colorado River as a real tool to manage our water supplies, which are on a downward trend. Not this year notwithstanding, of course, since we are in a very good situation this year. So with that sort of lead-in, I would look to my left here. John Katzenberger from the Aspen Global Change Institute is here. Maybe we'll just kind of go around and address those, your general reactions and how you see cloud seeding after today's presentations.
Okay, hello, John Katzenberger. Okay, is that on now? Yeah. Okay. John Katzenberger. I came here to learn about cloud seeding. Just read some of the literature over the years. A couple days ago, I had the opportunity to be with the former director of the World Meteorological Organization's climate research program, I think it's called, the World Climate Research Program. And I asked him about what the World Meteorological Organization studies have come to say about cloud seeding. And he pointed me to their website, but he also just off the cuff said that they've done studies in about 50 countries and over roughly 30 years. And actually NCAR has been part of that work. And his kind of off the cuff, a little bit cheeky comment was that it's inconclusive. But I think that what he meant is that overall it might be inconclusive, but in certain cases there can be efficacy that can be demonstrated. It's very difficult. And what I kind of, in talking to him further, what I kind of got out of it was if we had 2 elk mountain ranges that were equal and equal air masses coming toward them, and one of these elk mountain ranges we could seed and the other one we couldn't, then we could have a nice control and get some measurements that were direct. But we only have 1 elk mountain range, so I think that where we can turn to really learn more is the kind of thing that we heard from the NCAR modeling, where in a model you're simulating what might happen in the Elk Mountains under different conditions. And I would think that that would make a lot of sense to pursue in terms of answering the question about what would the efficacy be in our case. I think in general it's a really critical question because as you know, if you live here, the climate is changing, and the computer models that were used in the last IPCC report, when you look at what they have to say about Colorado, and this is represented in the Colorado study that Lucas did with the Western Water Assessment, that Colorado's already gotten warmer since World War II, 2 to 3 degrees Fahrenheit, and whether you look at the medium or high emission projections going out this century, Colorado will get a lot warmer, anywhere from 3 to 8 degrees Fahrenheit by 2050, depending on which emission scenario. So we're really entering a new kind of climate state. And so a lot of our ideas about what's normal, our snowpack, et cetera, is really going to change. We have a shifting baseline, if you will. We can't compare to some kind of 20th century sense of what's normal. So that makes for a really important problem to grapple with, because the same models also project precipitation is pretty flat, maybe a little wetter, maybe a little drier, and depending on where you are in Colorado, the further north may be a little wetter. But these aren't big changes, and maybe, plus or minus 5%. So from the standpoint of water resource, standpoint of snow pack, recreation. You know, we have a serious issue ahead of us, and I think that taking all of that together without actually investing in the seeding, we could learn a lot from the kind of work that was presented by the NCAR approach. And maybe after that, we could revisit the question. So that's kind of my take on things.
Great. Well, thank you, John. So in no particular order, I think we just keep going around the room, getting general reactions, if that's all right. And Rich Berkeley from the Aspen Ski Co. is up next.
Thank you, Dave. Our primary involvement with this is holistic. In spite of the fact that people think we don't live in the community, we are part of the community, and we would like to see a healthy river district from Independence Pass all the way to the Colorado. So that's the number one primary motivator for being here. Number two, we do run hotels in addition to ski areas, and a healthy tourist economy is the basis for our foundation, and having water seemed to be important to that, and so we support that through April Long. We also make snow in the fall. We make snow generally when rivers are at their lowest point, and having a healthy stream flow that avoids minimum stream flow restrictions is important for our snowmaking. It's a very small amount of water relative to natural flows, but very important for us to start the season. And then lastly, as a ski area in Colorado, generally everyone agrees more snow is better than less. So even if it's only 1 or 2 or 7%, we'll take that on a given storm cycle or in a given season. George, to answer your question specifically, we did a 3-year study. Actually, Larry drove that with Fred Smith a little bit before my time, but I was certainly on the tail end of it. Inconclusive was our thing, and I think 3 years wasn't probably enough time, and we didn't have the mathematical skills to take the noise out. But what you're seeing today, I think, is some pretty concrete evidence that the nucleation does work and that you're increasing precipitation. So that is the big change in the last 30 years.
Great, thanks. Andy Mueller is the general manager of the Colorado River District and my boss. Thank you for coming.
Thanks, Dave. I want to try to answer George's questions from the River District's perspective. Our interest, as DK said, is really in water supply, and it is not just water supply within our 15-county area that the district covers on western Colorado, but it's the water supply for the entire 2-country, 7-state basin, the Colorado River Basin. And we've seen a tremendous drop in the flows, the natural flows in the Colorado River over the last 20 years. We anticipate, based on the science that we've seen on climate change, that drop, it will continue at a rate, by 2035 of potentially a 20% drop in the flows. It is directly related to, or I should say indirectly related to, scientists can say this better, but Western Water Assessment has done some great work on relating the rise in temperature to the reduction in stream flow. And it's for every 1 degree Fahrenheit that we've seen a corresponding 4 to 5% drop in the stream flow. And from our perspective as an entity that looks at the entire basin, knowing that 70% of the water in the Colorado River system comes from western Colorado, every small percentage of water that we can add to that stream flow is important. I think it's important that if we're going to move forward in expanding our current cloud seeding, that we be open to and understand the tools that are available through NCAR and others that may help us understand the real efficiency in seeding this particular area in the Roaring Fork or other areas within the state. And those tools may lead us to a conclusion that it's not worth under a cost-benefit analysis to do that. My guess is it probably will come out and say that it is a reasonable opportunity to cloud seed. But I think we need to look at that. And I'd say, I think many of you have seen the work that Western Water Assessment did just on the Roaring Fork and looking at the drop in stream flow between 2000 and 2012, compared to that 2 degree change that we've seen in temperatures. There was a 3% drop in precipitation in the Roaring Fork Valley during that period of time, but there was a 13% drop in the flows in the river. and that's the native reconstructed flow. So what caused that is the question, and it's clearly the rise in temperatures having that impact. And so when we look at being able to seed, even if it's only 20% of the time between November 1 and April 30th, that 20%, if we can add anywhere between 3 and 10% additional snow water equivalent to the snowpack, it certainly isn't going to hurt our economy here in western Colorado, and frankly the health of the Colorado River and all of its tributaries. So we would encourage everybody in this room to continue to study this and hopefully move forward based upon sound science. So.
I want to first of all thank everyone for being here. As a county commissioner, I often find that when I walk into a room, I'm the least knowledgeable on whatever the subject is of the day, and that certainly applies itself here. We've been looking at this for a couple of years, and what I like is that we've taken it this far, and we actually have people who are doing science, and what the studies I've heard about have been demonstrated and shown to us today. I think that's very valuable. The questions still remain, and they probably always will, just how efficacious it is. I think the thing that my biggest takeaway from today was that when you're looking at the concentrations of silver that might concern people in these test areas, it's something like between a 5,000th to a 340,000th parts per trillion of what's acceptable for drinking water and for public health. So I don't think the issue that we should be concerned about here is the toxicity of these quantities of silver in being added to the environment. I don't think that's an argument that hopefully will help allay people's fears, because I know that's one of them. We have other toxins in our environment that are much greater, and it's not an apology or an excuse for adding more, but I think this is approaching unmeasurable and negligible, I believe. And so that's one of my biggest takeaways. Regarding the science and the need for more studies, I think we could keep studying things, and I'm always worried about doing more studies. If there was a proposal to do something here so we could get a better handle on it, great. I have a feeling that the people would argue that we might know enough already to take a stab at this. And so my suggestion would be maybe not to study it, but I guess my suggestion for today would be I want to hear from the practitioners who are doing it. We have some at the table. Slade's here, and who's been doing it to our west. We had the Vail people. Were they here? I'm not. Okay, we got our gentleman from Vail's here, who've been doing this for some in cases up to 40 years or more. And if they have anecdotal evidence, I still think it's worth hearing. So I'm looking forward to hearing more, and I'll shut up now.
Well, thanks, Greg, and I will introduce Slade Connell. He's an employee of the City of Grand Junction, but I think the chair of the Water Enhancement Authority, which is a collaborative effort that includes more than just the city, but the city has taken on the role of operating a cloud seeding program on Grand Mesa. So with that, maybe, Slade, you can give us some of your words of wisdom and experience on your program.
Okay, well, one of the things, because I felt the way you do, and I took this over like many of us in this room, does it really work? I took this over 10 years ago, and when we filed for a new permit, and we had one area in them. I don't know if you guys are familiar with the Mesa. Of course, it's flat, so it's different than mountains. I mean, it's a different scenario. We have control points on all four sides of it to where that we can measure any one storm, a month, or the whole season based on those control points. Now, it's not the same as, I think, what April was saying as far as flying right over it and seeing it. Actually, not April, the one.
Sarah.
Yeah. Sorry.
And you're speaking about the Grand Mesa, right?
Yes, the Grand Mesa. We go from Cedar Edge, Frost RV, all the way around to Vega Reservoir. 360 square miles is basically our target zone. So we have it set up if the wind's coming out northwest, northwest, every aspect. Now, here's the one thing that just to help you guys, I don't feel it's toxic at all. I mean, we've done sampling, we've done testing, because we've been, the city, of course. We have U Water, and we have all the other water districts involved as well, except I think Palisade. But and that was a big question. Well, are we going to take and contaminate? So we had to answer that first before we got them to come on board with us. So we did a lot of sampling. We never found nothing within our watershed, soil, snow. But the one thing that really brought us into it is about 2 years into this, because I'm beginning to wonder, is this really working? What are we doing here? Or is this a waste of time? You're just up here freezing, And when you're the president plus the chief of field operations, so you get to go out and fix it and do all that stuff too, which is fine because we've learned a lot and we save a lot of money by doing it ourselves. But the one thing that we did is, I don't know if you guys are familiar with Chambers Reservoir. It's way out on Indian Point, kind of like you're going toward Delta. And you look back up toward Wells Gulch. Anyway, it's just a smaller reservoir, about 170 acre feet, big flat area, feeds into it. And I thought, this would be a really good area to test because it always produced the lowest amount of snow, water, everything. So what we did is we set up a seeder. Now we have an Idaho Power seeder set up there. But before we did that, we set up a manual seeder just for that, and we only ran it when the wind for sure would hit that area. And it gave us an increase. We went off of what we did is looked at all the others based on the control points and the percentage of those control points and what the percentage of chambers was, and that percentage went up that year. And every year since then, it's maintained that within, just like all the rest, because there's more seedable storms this year. I think we had 22. Of course, we didn't seed the 1 or 2 inch storms. There was a couple we didn't. But that's what brought me into it, to help me to appreciate that, yes, this is very viable. It is adding water. It is adding snow. And it's not a waste of time, even though it's cold and you're up there. And it costs money, but at the same time, we can't live without water. And so since then, we've got 6 remote seeders that we run. We have an LPG, actually, and I don't know if anybody else has an LPG.
You gotta explain what it is.
What is that?
Liquid propane generator, not AGI, so no silver. We put it up high at frost. It's in the cloud, basically. And, of course, the wind and whatnot criteria there is a little different than an AGI, but our meteorologist tells us the same thing. We turn it on. And then we have 5 AGIs, and then we have 14 manual. And the meteorologists call and have those guys turn them on. But one of the things we did is we went in and we bought those 6, and then the other 14, I was mentioning to you that we used to have those 8 gallons, and most of you probably don't have 8-gallon seeders still out there. These are from like 1970. I mean, they look like a grenade. But they worked, and they still work. But we were finding that we were having to fill them like 2 to maybe 3 times a season. And so we went to 15 gallons, doubled them, bought brand new ones, titanium. And now we've got some 21 gallons, and this year we only filled them 1 time, which saves on your overall maintenance costs, this and that. But your solution's still the same. Still putting out the same amount. We use, basically, just to answer your question, to give you a little better idea, when we set the needles manual, and maybe Eric has an idea on this too, we usually, basically 10 hours is 1 gallon of solution. Is that what you find? Close to that? I mean, it's give or take. Mm-hmm. Somebody has real big fingers, a quarter turns, half turn. So you just use, but that's pretty much what we've found to be the case. And so that's why we went ahead and, working with CWCB, we went and bought all of our equipment. It's not rented from nobody. We own, operate it. We pay the meteorologist from Montrose, and we have the permit. And we go out and do all the maintenance on our, whether it's DRI, Idaho Power, which they help us. I mean, there's some major things that if we need to, we have a contract thing where hourly we can just, and Brandl's been really good at working with us, and we let them deal with that. But
so what kind of results do you think you're getting? What are you recording?
Again, ours is a little different than what Sarah did, but ours has the control points that the state dictated to us when we did the permit 10 years ago that are unseeded areas, that are so-called equivalent to our area, flat top. And we've been seeing approximately, again, flat top may make a difference, 15 to 16%. Now, our meteorologist can do it per storm, or he can do it per month, or he does it per year. Well, when we turn in our yearly report, This year it happened to be 10% because Mother Nature pretty much did most everything for us. Even though we seeded, we didn't get as much out of it compared to what she did. But on a normal case, we're right around 15 to 16, and we have never been below 10 based on those 4 control points in seeding the storms.
Is that annual snowpack or?
Annual.
Annual, okay. And then what was it last year in the drought year? You said that.
In the drought year,
how many times did you?
We seeded 8 times, so there was not many storms, but we still took the control points with those 8 storms, what they got, what we got, and we still saw a 16% increase of what we, kind of like a sponge, squeezed the rest of that water out of there. And so even with that 16% is not like the 10% this year. 10% this year far outweighs that. But that 16% was still, it's another drop, 2 drops, 3 drops, whatever it was. It still was more water. So that basis plus the one that we put in there for Chambers helps me to appreciate that this is something that I see that everyone's going to be, I'm not going to say forced to do, but as you have the climate change and have more people moving into the western slope and you need more water, we have no other options really. So I see it as being that. And when we went and talked to Ute Water and Clifton and all those guys, they seen it exactly the same. We showed them the results. We went before their boards and did a presentation, and they all bought into it, and there's some of the local donators, and then the CWCB helps us as well.
Great. Well, thank you. Thanks for that.
Yeah, and thanks for coming, Slade, and letting us know how that works. And you mentioned CWCB a few times, and next to you is, and CWCB, for those that don't know, Colorado Water Conservation Board. The program manager for cloud seeding is Andrew Rickert. Maybe, Andrew, you can, since you're very familiar with the data and the information anyway, how does the permit work when you work with somebody like Slade or with the Central Mountain program like with us? Maybe briefly you can kind of go over the what it would be like for Pitkin County should they opt in to a new permit.
So right now Colorado has 8 permitted programs. 7 of them are ground-based, and our newest one in the Never Summer Mountain Range by Walden is the first aerial. The first thing we do, if you guys were interested, is we have you run notice of intent in the newspapers in your county and all adjacent counties for a minimum of 2 weeks. Once that's complete, within 1 week of that, we hold a public forum, basically, where the sponsor needs to come. You need to have, here, I wrote some of this down. Obviously, whoever's going to operate the program, operational plan is complete, proof of financial responsibility, project sponsors paid the permit application fee, provide proof of publication of public notices, and we have all this information on our website, but basically that's the time where the project sponsor would come and basically give an overview of what the program's intended to do. We'd have a public comment portion of the meeting where any concerned citizens could express their doubts or opinions. And then as a state agency, we basically look at all the information provided and decide if it's going to be an efficient program and whether or not we should issue the permit. And then we will issue a record of decision from that public forum process, and then we will issue the permit.
Now, I just want to be clear, who would actually put the permit in? Because I understand it's not up to the county or the city of Aspen or
the operators of it.
The operators. So the company or would CRD, who does the
So
permit?
right now,
who holds the public hearing?
The public hearing would be held.
I would hold the public hearing.
But the sponsor, whoever that sponsor is, the sponsor could be city, county, district, or vendor. In our case, in the Central Mountains, it's the vendor. And so they do the advertising, they respond to, or they pay for the advertising, excuse me. They respond to the requirements, and they operate the permit. And you should probably be answering this, but pursuant to the regulations that the state of Colorado under the Department of Natural Resources has promulgated. So again, it can be anybody. It could be Pitkin County if they wanted to be the sponsor, and they could delegate the operations. For the River District, again, we work with the vendor. The vendor, in turn, takes the responsibilities and liabilities inherent in the program and complies with the regulations.
And just to, just to be clear, the River District is willing to administer the program in Pitkin County in the same way that we work with the vendor to administer the Central Colorado program, to wrap it into that.
So it'll be part of that program.
We wouldn't suggest that you have to go out and get a different, you know, I think we can modify the existing permit to include this area.
It would be a new permit.
New permit, but we would operate it, we can operate it together so that you're not looking at additional human resource costs in the county.
Okay.
So.
Yep. Thanks for the clarification.
Has any permits ever been denied, or you just have those 8 and they've all been approved?
Correct, yes.
Just wondering if so, why?
They do have different criteria on each one of those permits in terms of the periods where they have to stop, the very site-specific avalanche issues and safety issues and flood control issues. But
And then all the criteria is in state statute that the CWCB enforces.
Any other questions or discussion on that process? George, you good?
No, it's great.
Okay, great. Just want to make sure we're covering everything. We're coming towards the end of our circle here, and coming to the City of Aspen and Root Eye Water and Power Authority. April Long represents both those entities today, and maybe you can give us your reactions.
Yeah, so similar to George, I had kind of the same concerns coming in, environmental impacts, both positive and negative, and then the cost-benefit analysis. And so I'll talk about that from the Clean River program in the City of Aspen's perspective. So thinking about the environmental impacts and hearing the answers to the questions that I had today, you know, we have background silver in this area, but we still don't see that as an impairment on the river. What we do see as an impairment on the river is low flows. And so we are listed for aquatic life. We have several reasons for that listing. Some are due to urban stormwater pollution, but also due to the fact that the river's heavily diverted, and so we have just severely low flows during our summer months. And with that, you know, the impacts to the river, be it temperature increases or discharge of pollutants, are much more exacerbated during that time. And so the city's been working really hard on ways that we can improve those flow conditions. And you know, the only way to do that is to begin to manage water differently, and that means sharing water differently. And so everybody has to make a sacrifice, and everybody has to give something up when you start sharing water differently. What I love about cloud seeding is that even if it is just a small amount, it is something that doesn't require anybody to share anything. And so you don't have to have any of those fights or conversations or negotiations, and you don't have to work through the legal issues or the physical issues of trying to get more water into the river system. And so though it is a small amount, I see a tremendous cost benefit for it in just that simplicity of it's the only way to create more water into the system. The other thing that I like about it, and I don't know that we touched on it very much today, but it is something that I've heard in past presentations about cloud seeding, is that, you know, cloud seeding doesn't work super well, like you were saying, in the drought years. So what's interesting on the section of river in the City of Aspen, this section that's impaired, is that during drought years, or during the driest of years, is not when we need water in the river. Because of the way senior calls work in the water rights system, those senior calls begin to come on during those driest of years, and water does come down our system because diverters are called out. And so it's in these kind of like moderately dry years to average years where our river is still in this dire situation, that this could have this impact. And so I think that cloud seeding during those years would be really helpful for us and helpful for the river. I think that, you know, it's up to our city council as to what the cost benefit is for this, but kind of going back to, this seems to be a really relatively low cost, especially split between the City of Aspen, SWEA and Pitkin County, compared to the other options that I have presented to the community and to council before about ways that we can improve flow or increase flow in the river. So this is extremely low cost compared to those types of situations. So that's what I have to add for it.
Just one other thing that may help too with the cost, which we did over there, is of course working for the city of Grand Junction. You have Ute Water. We can't take any of those employees per se and say, okay, here you go. So we had to form this company, and of course they allow us to, and then that's where the insurance and all goes through it. But then with that, we have like those little ditch companies. They'll give us $100 a year just because it enhances what little bit of water they can get.
Right.
Those ditch companies we've got them on both sides of the mesa, and we didn't think of that at first. Actually, we went to the ski resort, Powderhorn. They help us. The water municipalities, but those ag individuals will help just as much. They may not be able to afford as much, but they'll be just as eager to help, so that might help offset it as well.
Oh, that's great, yeah.
And another thing that we do have, which I don't know if you'd be interested, if you're just going to do this as a trial thing, I had talked actually with Joe about it, doing it with Gunnison, but it didn't work out with them. But we have those 14 manual seeders that are still operable. They're the ones I said, they're grenades, they're 8 gallons, they're still operable. They may need a little attention since we bought the new ones, but they work exactly the same as the new ones. And so you wouldn't have the cost of renting or buying those up front. You put your solution and have your operators and turn them on. So that's an option as well. I mean, we're not using them. I mean, I'm willing to help you out with that if you want.
Thanks for the
you
offer.
know, I mean, it's more water in the river, so, and they're just sitting there, so you might as well use them if you're not sure, you know what I mean?
Yeah,
if you're sure, then
appreciate it. Appreciate the perspective.
Great.
Let's keep. But
Yeah,
thank
we'll
you for that.
keep moving. Lewin. Thank you very much. And so, Heather Lewin from Roaring Fork Conservancy's next. What would you say if Slade gave you a bunch of cloud seeders? How
to you
for their conservancy, would that be a good thing, a bad thing, and how do you see cloud seeding in the context of watershed health?
You know, I think we come to this with similar concerns that we heard from Rich and from Andy about the receding snowpack we've seen and the subsequent impacts you see to streams, to stream health. April talked about a lot of the specifics of that. And so I think generally we'd hold to that same idea that any bit more that we can do is probably going to be beneficial or is potentially beneficial. We heard that generally this silver iodide's not a water quality concern, but one of the first presenters mentioned that maybe it'd be a good idea to have a controlled study going on anyways, and I'm not sure which one said that, but I had written it down. And so the thing with silver ions and silver iodide, maybe the city might have more on the silver ions, but I talked to our water quality coordinator during the break, and he said we don't have very much data. We don't regularly collect data on silver ions and none at all on silver iodide. So there isn't any sort of baseline foundation at this point. And so I think that would need to be thought through a bit in the process. I think the modeling itself is fascinating to try and figure out what the potential of this is. I'm curious whether, and maybe Dan, you'd be able to answer this, whether cloud seeding changes the snow water equivalent. Does it change the density of the snow that falls or just the quantity of the snow that falls?
Is your mic on?
Does that question make sense?
Yeah. And the simple answer is that you wouldn't be able to tell the difference. The more complex one is there might be periods of time when it, if you talk about crystal type of kind of what happens naturally and then what happens with seeding, you might get a little more rhyming and then it might be a little more dense, but I doubt that you would be able to see any kind of difference really. And maybe my other colleagues here would have more insight into that.
With the colder storms is when you see the greater amount.
We need a microphone, sorry. Okay, turn off the mute if you would.
I'm Larry Germstead with Western Weather Consultants. At the colder temperatures is when you tend to see more visually the difference or the impact of increased snow, because the crystals are maintaining their identity better and stacking up, where in the wetter storms, a lot of that extra moisture is you only see it in the snow water content, in the SWEA numbers at the SNOTEL sites. And that's what basically we've seen in the evaluation that we did at Vail, both inches of snow and the difference in the snow water content.
Well, we're rapidly approaching 5. We have 2 more. Are you good? 2 more speakers in 2 different perspectives that I think are valuable. We have not touched on today. That's forest health and wildfire management. And to talk about forest health is Adam McCurdy from ACES, the Aspen Center for Environmental Studies.
You got it. Thank you. We're good here. It was a really interesting day. Thank you, everyone who presented. Really enjoyed it. I think from a water supply side of things, this seems like there's a lot of really good research and it makes a lot of sense. Obviously we didn't talk about any of the land-based ecosystem implications, and I haven't seen much research in that realm. So I would have additional questions just from kind of my perspective in terms of how much more water is that putting on individual parts of the landscape, and I guess even more importantly, one of the things we're looking at with climate change here in the western U.S. is the earlier melt-off of snow. And so how much would cloud seeding push that back? And especially for us in Colorado, we've got this gap in June, one of our drier months, where if we push that snow melt back, then we have a longer dry period before the monsoons start coming in. And we know that our forests have suffered quite a bit. A lot of the different beetle activities, the pine beetle, spruce beetle, Doug fir beetle that we have in the valley, are all connected to heat stress and lower water availability. So I'd be curious if it has any potential to help any of that, but no idea. Yeah.
Great. Well, thank you for those comments. And finishing up here is Charlie Curtis. He's with the Aspen Fire Protection District, and your reactions, Charlie.
It's nice that I went after Adam, actually, because he kind of mentioned some things that are relevant to what we would consider for wildfire. And one of those things is the ERC, which I think Greg included on email for us to consider. Or it was you?
Define it.
Okay.
Can you define what that is?
Oh, ERC being the energy release component, basically the fuel potential of the fuels, trees, vegetation in a forest. And really my only experience with that is directly with wildfire, so I don't know if they use that in forest health at all.
It's one of the
factors. But basically, in my opinion, working with some wildfire here, things that affect wildfire potential and danger has probably more to do with wetting rain during a wildfire season. So snowpack wouldn't really affect our season, potentially pushing it back a little bit. But even this year with high snow totals, we're still in considerable risk for wildfire. It just might be a little bit later, because once we start getting to the drier months, all that fuel is still potentially going to go up. Other than that, I think more water might have the potential to make more fuels out there. But again, I don't think if you're limiting the amount of seeding you're doing to sort of natural or to mimic sort of average snowfalls, you're not going to see any sort of extra loading that would be of concern.
Well, great. That kind of takes us to the end of our roundtable. I'm going to look out in the audience for any last-minute questions or concerns. I'm seeing none. I'm seeing one comment. You got to come up, please.
Come up to the mic.
And we are after 5, so we're going to try to keep it brief and wrap up here pretty quick.
This will be real quick. About the comment about the silver iodide toxicity analyses, trace chemical stuff.
Oh, mute the mute button.
Oh, did I hit the mute button? Darn it. You guys caught me. All right. Anyway, about that comment about the toxicity study, I made it because I think it's worthwhile to do because, like was noted, there is a very small data set. There's few studies about that, even fewer in this area, and I think it's worthwhile to get a baseline for it. And period. That's why I mentioned it.
And we, the River District, do have a cooperative monitoring program with USGS. We do monitor for trace metals in the main stem of the Roaring Fork, and so there is some baseline data, and I would agree and work with those interested to expand that monitoring program as needed, as desired. So that brings us to the end of a long day of a lot of information. I really want to thank you all for hanging in there, for those that have traveled, and just a quick reminder that we are going to try to archive all this valuable information on the River District website, team up with Pitkin County to make it available. The live stream will be archived, viewable on Grassroots TV, and also, again, viewable at pitkincounty.com under Watch Meetings. So thank you very much again for your patience. Any other last words from the county?
Other than thank you all, and I think the plan on my agenda is to adjourn to the tap room over here at the brew pub for a beer if you have the opportunity. So I think we should do that post haste.
Post haste and continue the conversation. Thank you so much.
Thank you all.